Howdy, everybody. Welcome, welcome. Happy Monday, happy Monday moron stream day. Fair. It was not Crazy Train, no. Close though, kind of. Yeah, it was my birthday yesterday. It was pretty good. I had a good birthday. I spent the evening after sunset staring at the sky, waiting for it to get dark, and inevitably wasting my time until like 9:30, which is kind of a bummer, but that's okay. Oh, Twitch does have the wrong title. Good call. Flat Earth. There we go. Twitch has been fixed. I am 33 now, yeah. What's on the other side of the flat Earth? That's a really good question. What is on the other side of the flat Earth? Oh, that's funny. Ooh, spooky green screen. Oh, spooky. Oh, you can see through it. From Grimlock with the $10 for plane tickets are getting pricey hydration. Fair enough. Thank you so much. Yesterday was your father's birthday. Well, then we share a birthday. You're gonna be in NYC for Comic-Con? I will? No way. Well, oh, do I want to go? Oh, why would Pangburn schedule it on the same day as Comic-Con? That's crazy. That's crazy work. Maybe though, maybe. This is what flat earthers think NASA does all day. True. A flirt Ludwig Strassenhaus was on Jovan's stream calling him. Oh, that's rough. I don't know if I've spoken with him. But that's mega cringe. All right, well, we have our first guest. Let's bring him up. Bring him up.
Yo.
Dot, how's it going?
Yo, fuck Charlie Kirk, alhamdulillah, inshallah, mashallah, he got cooked, he got cooked.
I don't know why they, I mean, okay, I get it. I get why they try to say their troll bit super fast. But like, well, I would never say that I agree with that person. But like, hey, how's it going? Afghan man.
No, I'm gonna go to sleep. Good night. I just want to tell you good night. I'm asleep.
Okay, good night. Weird. Tyler Hop.
Yo.
Tyler Hop, how's it going?
I just came to ask, bro. When are you doing some more God debates?
Probably Thursday and or Friday.
Alright, yeah, I'm gonna join in then.
Okay.
Alright, see ya.
Let's talk to Genghis Twan. That's a name. Genghis Twan, how's it going? Okay. There's an echo? Echo, testing echo. I don't know where the echo is coming from. Testing echo? I don't hear the echo. I don't have an echo on my end, and I'm not actually even seeing it on... Okay, so there's no echo on TikTok. Guests are echoing. Ah, okay, that I can potentially fix. It's only from colors? Okay, yeah. So next time there's a color up, I can probably fix it. I just have to find the... right audio, or the right... You know the bar that gets green and then yellow when people talk, and then it stops being green and yellow and like gets bigger, and then like the there's a word for it. It's like the audio mix thing. There should be two that go up if there's an echo. So I just have to turn off one of them. I suspect it's that one though. The green, yeah, exactly, the greeny yellow bar. It's not quite a slider. You don't slide it. It slides on its own. Equalizer, something like that, yeah. Alright, let's talk to Wesley Snipes. Wesley Snipes, how's it going?
I'm good, how are you?
I'm doing alright. Is that the real Wesley Snipes?
Nah, I'm his twin.
Oh, you're his twin. Crazy. Okay, so Wesley Snipes, what shape do you think the Earth is?
I think it's flat.
Okay, why do you think the Earth is flat?
Because if you look straight ahead, it just looks flat.
If it looked flat, then things wouldn't seem like they go down in front of you. What's the deal with that?
Nothing
Sure it
looks
does.
like it's going down. Everything just looks straight.
Apparently, you've never looked at anything far away.
I have. It looks straight.
One sec.
It looks like it just continuously goes straight.
1 second. And we can just look at this together. There's a really famous picture. So if I show you this, that kind of looks like it's definitely curved. Doesn't look straight to me.
That's just distorted by the image. Like the image that they took, it just distorts it. But it's actually straight.
Oh, okay, so when people say that this is what it looks like, they're just lying.
I think they just see an image distortion, how the light reflects off the water, and the water reflects onto the...
I'm sorry, I thought you said that it looks flat, but if it doesn't look flat, then where do we go from there?
It does, but like water affects it a little bit.
Oh, okay, so it doesn't always look flat.
It doesn't always look flat, but like only if water distorts it.
Okay, so it seems like you're reasoning that it looks straight, that it looks flat, it just isn't true? At least not always?
Yeah. Normally it looks flat, but like when water...
Except when it doesn't?
Except like when water comes into equation,
So like most of the time? Because most of the Earth is covered in water.
No, it's not.
What, you don't think that there's more water than there is land?
There's more land, obviously.
You think that there's more land than there is water?
Yeah.
Have you ever flown across the Pacific Ocean?
Nah, not yet, no.
Okay, the Pacific Ocean is all water, right? That's what oceans are made of, right?
What?
Did you know that oceans are made of water?
Yeah, that's like, I think that's what they're made of. Like they're blue.
Yeah.
So like,
and so like when you fly, you can fly across the Pacific Ocean for like 12 hours and you won't see land.
No,
and you're telling me that like somehow Earth is mostly is mostly land?
It's not saying it's mostly land, I'm saying like 50-50.
No, it's definitely like 70-30. 70-30 water, land.
I think you're confused, man. I think you're actually confused.
I can assure you I'm not.
Like, I'll teach you something, okay?
Yeah, please.
The Earth is half and half. Otherwise, the magnetic resonance of the tectonic plates don't match up.
Oh, you're not a flat earther. Flat earthers don't believe in tectonic plates, but good troll attempt. I appreciate the effort.
Nah, I do believe in tectonic plates, but like tectonic plates are part of like what keeps like the Earth is flat, but these tectonic plates they move up and down. So like they just only move up and down.
The effort is the recovery attempt is goated but insufficient.
Wait, what?
The recovery attempt is goated, not insufficient.
I genuinely believe like the Earth is flat. I don't know why you think I'm trolling.
Oh, okay, then what are tectonic plates?
They're like things that go up and down that push the Earth up and down.
Oh, okay, and what causes them to do that?
That they move in it. It's like God makes it happen. I don't have an explanation. God makes it happen.
Okay, Wesley Snipes.
You don't.
Okay. Okay, Wesley Snipes. I mean, he was obviously trolling. They're escalators. No, he was definitely trolling. El Cine, how's it going?
Hey, how are you? Good morning. I'm 39.
Glad to hear it.
And I'm a flat earther.
Okay, why
yeah.
do you think the Earth is flat?
First of all, because the Bible says it, and the movies gives us clue, like the show of Truman, Maze Runner, and stuff like that.
Movies give us clues?
Yeah, because...
What would movies have to do with the shape of the Earth?
And the Bible verses, especially the Bible verses.
The people who wrote the Bible definitely thought the Earth was flat. But, like, we're more advanced than them. So, I don't know why we would take their word as gospel, if you will. The irony is not lost on me.
Okay, but why we see the Northern Star and the Northern Star doesn't move?
Why do we...
Always...
Sorry, are you asking why do we see the North Star and why doesn't it move?
Yes.
Well, so why we see the North Star is because we're in the Northern Hemisphere. I assume you are, otherwise you wouldn't see it. Why it doesn't move? Well, it does move ever so slightly, but the reason why it doesn't appear to move to, the human eye is because it is basically exactly where the axis of, it's in the exact direction of the axis of rotation. So, like, imagine that you are, standing on top of a spinning top, and there's a light directly above you. Well, regardless of where you are on the spinning top, the light won't look like it's moving. Because it's directly above you, right? It's not like off to the side, where if it was off to the side and then you rotated, it would look like the light would look like it's moving. But keep in mind, people in the Southern Hemisphere don't see the North Star, which, is very, very strange if the Earth is flat.
Okay, good point. But in the music Californication, it says that the space is the final frontier, but it's made on Hollywood station. So even the songs gives clues. But I know that it's more conspiracy theorist than science. So most
I want to think that you're trolling, but I don't think you are.
Yeah. I know that 5% of the world population are flat earthers. But I'm a Christian, so I believe in the word of God and not the word of humans.
So that's what do movies and songs have to do with the shape of the Earth?
Because we believe that Freemasons put us some clues. So
why would they do that?
So they cannot get karmic retribution. The Freemasons know the truth about the Earth.
Why would they give us clues?
So they have not get a karmic retribution. He has to say something.
Why wouldn't they get karmic retribution just because they give us clues, even if they're lying to us?
Well, I think that Masons give us the truth. Like 9/11, there are many predictive programming. The 9/11, the September, 11, the Twin Towers.
No, I've never heard of this. Tell me about it.
Yeah, The Simpsons, the passport of Neo was in 9/11 in 2001. Stuff like that.
Is your entire worldview based off of like movies and TV shows and songs?
Yes, sir. And the Bible, especially the Bible.
Wait, did you just say yes, that's your entire worldview? It's based on that?
Yeah, I'm a conspiracy theorist. I'm a Christian and a conspiracy theorist. I wonder, you didn't talk about those kinds of people, the flat earthers? Most are Christians and conspiracy theorists.
Yeah, but like, why not just actually believe like the evidence rather than relying on movies and TV shows and music?
They believe that we are living in a conspiracy world. Like I showed you,
Oh, they believe.
Wait,
that... I'm sorry, they believe that, so you don't.
And we believe, and also me.
All right, Alcini. Go on, get out of here. He outed himself as a troll. All right, let's bring on your. How's it going?
Yo, it's good. My question is, why are you giving platform to people who oppose science?
The same reason why I'm giving a platform to you. Oh wait, I'm not. So it turns out giving someone a platform so you can make fun of them is like actually, especially if like they're bad people or if they, you know, are making the world a worse place, is actually a good thing. It turns out that that's actually like a morally good thing, a morally oops, there you go. A morally virtuous thing, if you will. So it seems like that we've banished all the flat earthers. The flat earthers have all fallen away. They've converted to what is the story of truth, story of light. They now believe that the earth is a globe. And if you don't believe the earth is a globe, then I don't know, man, you might have to come up and defend the shape of the earth.
Hello?
Your name is Bleed in My Cup. It's an interesting name. Bleed.
Oh yeah, thank you.
What shape do you think the earth is?
Oh yeah, well I basically think it's flat.
Okay, why?
Well, for starters, so when you look at the map, right? When you basically look at the map, it goes in like a diagonal shape of the 3.7 meters. If you could like, cause you might, it's kind of hard to explain. Do you know what I'm talking about or not?
Either you're like mega intoxicated right now or you're just trolling. Those are like roughly the two options.
No, I'm not. No, I'm not.
What shape do you think the earth is? Like what map do you use?
What
map do you use?
The globe. Well, no, not the globe. It's like, yeah, I use the globe.
Okay. Goodbye. Let's talk to Dominic Hubbo. Dominic Hubbo, how's it going?
Good.
Dominic, what shape do you think the earth is?
Oh, I think it's round.
Dominic, you realize that A, you have to be 18 plus, and B, this is for flat earthers, right?
Did I ask?
Let's bring up this person whose name is unlisted.
Oh, yo,
no
my
name.
bad. I didn't know I requested. I'm sorry.
You're good. Okay, let's talk to Tybring. Tybring, how's it going? What shape do you think the earth is?
Good. What about you? I think the earth's flat.
Okay, why do you think the earth is flat?
Because I'm a part of this group.
When you're off the app, I can't hear you.
I'm part of this group. It's called, sorry, can you hear me now?
Yeah, I can. If you say neo-libertarian phalangist, I'm gonna cry so hard.
No.
Okay.
So, essentially, they taught me that the earth is flat because of gravity.
Good troll. Let's talk to Raul Alvarez. Raul, how's it going?
Oh, it's going pretty well.
Glad to hear it. Raul, what shape do you think the earth is?
I'm not really sure. I've seen a bunch of lives about this. I always like to believe, what is proven to us every other day, right?
Mm-hmm.
How the horizon, how it curves, how the sun, we have sunsets and sunrises. So it makes no sense why people think that the earth is flat, but
I agree.
I'd like to,
But you're still on the fence.
No, no. I mean, I'm more over at the globe, right? The shape of the Earth is globe, not flat. But I wanna.
Well, Raul, I
really
gotta let
like
you go then, because the live stream does say opposition only. And if you want to learn about the arguments for the flat Earth or for the globe Earth, then you can pay attention. Morpheus, how's it going?
Hey, good, good. I want to see if we can finish up this last conversation we had.
Did we speak? Have we spoken before?
It was about 2 months ago, and live just shut down on us because I had you in a corner, unfortunately.
I'm trying to see. Oh, we spoke on January 22nd. Does that sound right?
Yeah, it could have been.
Like 5 months ago. I don't actually remember talking to you, but yeah, we can. Actually, you went up on the YouTube channel.
Okay.
Did you know that?
Oh, nice.
So, why do you think the Earth is flat?
Well, here's the problem: is that when you accept the gravity model, it doesn't make sense. You have two different models. You have a model apparently for space, and you have a model apparently for Earth. And
yeah, can you elaborate on that? What do you mean?
Well, when we accept gravity, we're supposed to expect mutual attraction.
Mm-hmm.
So when we're told about planets, we're told that planets are attracted to each other, right? So when we see astronauts in space, they tell us that they are floating because of free fall. So what I'm trying to explain here, how do you have the effect of free fall for astronauts, but yet on Earth we have stable ground, and we don't see any of that. We don't see any free fall effects on Earth, but we know
if you're falling, you are experiencing free fall.
I understand that, but so I'm in a chair right now. How do I expect to see free fall if I
can drop something?
In a chair? I understand, but
if you are not experiencing free fall if you're sitting in a chair.
Okay, so let me ask you this question.
Please.
If you are in an airplane and it drops straight to the ground, are you in free fall inside that airplane?
At least until you hit terminal velocity. Initially, you would be at free fall, but there are other forces involved, so you're not going to be exactly in free fall.
Okay, but what I'm saying is that when we look at linear motion, we know, or you tell us that we don't know that we're in linear motion. We know that, but in free fall,
what do you mean by linear motion?
When you say that we're in a plane and we go 500 miles an hour,
sure,
you tell us that we don't notice it, right?
Yeah, I mean, I can sleep on I wish I could sleep on a plane. I can't sleep on a plane because I can't sleep while sitting up. But people can sleep on planes. We can have a cup of water sitting on a table. And so the cup of water is going to behave exactly as if the cup of water was sitting on the ground. It's just going to sit there. It's not going to be rippling. It's not going to be pushed back or anything. It's just going to be sitting there. So yeah, I mean, barring turbulence, of course, it is going to be indistinguishable from just sitting on the ground.
But that's the whole point. If you're in free fall on an airplane, you're going to know that you're in free fall. Is that correct?
Well, so it just depends. I mean, the reality is that the reality is that so free fall happens when there are no forces on you except gravity. But we live on a world with an atmosphere, and that atmosphere can cause drag. It can cause all sorts of these kinds of phenomena that would make your motion noticeable. So, for example, if you're just driving on the road and it's like a straight shot, right? The highway is just like a straight shot. If there's no bumps on the road and you have good shocks, it'll feel like you're not moving. But the moment you stick your hand out the window, all of a sudden your hand will be blown backwards because of the air. Yeah. And so the effects of the atmosphere can absolutely make your motion appear or make your motion feel like it's not, at rest, or make it seem like you'll actually notice the motion, if you will. But that's because of the air. It's not because of the motion, right? It's because the air's there. If you were in a vacuum, you wouldn't see that happen.
Yeah, but that's my whole point. Everything that you're describing has a effect that has nothing to do with the rotation of the Earth or gravity. You're giving me air excuses. You're giving me putting my hand out the window, but that doesn't correlate to any of these mechanics that you're telling me that I'm dealing with. Right?
I'm sorry, what's the objection?
When you're saying that I'm putting my hand out the window, you're saying it's because of the air. Is that correct?
Yeah, of course, and that makes sense, right? You can feel the wind on your hand.
we all understand that. But if I'm sitting in a chair and there's no wind and it's just a day where it's just really light outside, where does that correlate to gravity or rotation or anything with that? Because we could just look at the weather and say,
to be clear, gravity and rotation are different things. So I'm not. I understood that we were talking about gravity. You're bringing up rotation. I don't really understand the correlation here.
Well, the problem is that here's what I'm going to say. Back to gravity. They tell us that astronauts are floating because of the apparent free fall motion that they're in. Right?
Yep.
That's what they tell us.
Yep.
What I am saying is that we're on stable ground. So there's nothing that tells us that we are in free fall on Earth. Right?
We're not in free fall.
There you go. We're on stable ground, sir.
So when we're not in free fall because there's forces acting on us.
But that's
besides
the whole point.
Gravity. Free fall only happens when the only force acting on you is gravity. If there are other forces involved, then you're not going to be in free fall.
You could say whatever you want, but ultimately, if you're going into a building designer, if they're building a skyscraper, they're going to have to take the assumption that the ground is stable and not moving. Would you not agree with that?
So stable and not moving they're not in conflict with each other, right? For example,
that's what the ground is doing, though, sir. It's not moving and it's stable. That's how they're building a skyscraper.
It's not moving relative to what?
It's just not moving.
Relative to what? Motion is relative.
To the tools, relative to the tools and construction equipment.
Yeah, sure. But that's because the tools are on the ground and they're moving with the ground relative to the center of the Earth.
That is not true, sir. They have to take
that's an assertion.
They have to assume that the ground is stable. Are you not assuming that?
The ground is stable relative to them, sure.
Sir, it's stable, though, at the end of the day.
Stable relative to what?
It's not moving.
Relative to what?
Relative to the building not tilting forward or backwards.
Yeah, so things on the ground are not going to be moving relative to the ground unless they have wheels or something like that, right?
So let me ask you a question.
Like if you build a building, of course the building's not going to be moving relative to the ground.
If I took your logic, then we wouldn't be able to notice earthquakes because I'm moving with the Earth, aren't I?
So what you notice in earthquakes is not the Earth moving, you notice it accelerating. Acceleration makes you feel...
What?
Hold on one sec. Acceleration, like when you are suddenly accelerating, that produces something called a pseudo-force, which is because you're no longer in a non-inertial reference frame, you experience, or your body moves in a way that your body wants to move in a way that would be inertial, except your surroundings or whatever you're attached to are non-inertial, and so you feel something that appears like a force. So that's why you feel an earthquake. You don't feel an earthquake because the Earth is moving. You feel it because it's accelerating.
Okay, that's fine. But what I'm saying is that we notice earthquakes, right?
Yeah, because of the acceleration, not because of the motion.
That's fine. You can call it what you want. But what I'm saying is that we know that the Earth is not moving. We know that.
Why you could say that, but like, why should I believe that at all?
Because we know that when the ground is not moving, we have no earthquakes.
When the ground is not moving, we have no earthquakes? Yes. What?
Yes.
I don't see how that
we
is
know
related.
The difference. We know the difference between having an earthquake and not having an earthquake, right?
Yeah, so if the whole Earth was moving in one direction, you wouldn't notice that, right?
The Earth is not moving, though.
Okay, but that wasn't my question. If the whole Earth was moving in one direction, would you notice that?
If it was in free fall, you would. Yes, you would.
That wasn't my question. If the whole Earth was just moving at a constant speed in one direction, would you notice it?
In a linear direction?
Yeah, in linear
according
direction.
to your model, then yeah, you probably wouldn't notice it as much.
Okay, I'm asking what do you think would happen?
If the Earth was moving linearly?
Yeah, like let's say that the whole Earth was moving. Okay, so you think that there's a firmament, right?
Here's the problem.
I'm trying to steal menu here. I'm not trying to straw menu or anything. So like, you think that there's like water around the firmament, right?
Well, I don't really like to get into that because I like to really talk with the shape of the Earth. I mean, that's
right.
More
But look, I'm not trying to straw menu. I'm just trying to set up a hypothetical just so that we can.
Go ahead. Yes.
So suppose that there's water around the Earth, and that water's not moving, right? And like the Earth is like surrounded by a firmament, and it's like, so imagine that like the firmament is like protecting us from the water, so we wouldn't notice if like the firmament was like buffeting against the water. Imagine that the whole Earth, including the firmament, was moving through the water upward at a constant speed. Would we notice it?
If it were moving, we notice when things are going up and down. Yes, we do.
Well, I'm not talking about going from rest to moving. We would notice the acceleration, of course, like in an elevator. I'm talking about, would we be able to tell the difference between it moving upward at, say, 5 miles per hour at a constant speed forever, like it's been doing that since the dawn of time?
You would.
How would we tell the difference between that and just not moving at all?
Because I'll explain it to you. If you were in an elevator, and it went up forever, and let's just say at 50 miles an hour, you're going to notice it until it stops. You're going to notice that you're going up.
How would you notice that you're moving upwards if it hasn't started and it hasn't stopped since you've been born?
Because we know that when the elevator wasn't moving, right? There was no motion or any forces to us, right? We can assume that, right?
No.
Yes or no?
So Morpheus,
if you're in an elevator
and maybe I can just give you a better thought experiment.
Can we assume that it's not moving, sir?
What motion is relative, but let me give you a perhaps better thought experiment. Suppose that you are you're knocked unconscious, right? You're given anesthesia or something, and then you're placed into an elevator while you're unconscious. The elevator has no windows. It has no they seal the doors. It's soundproof, whatever. And then the elevator just starts moving upwards at a constant speed of, say, 10 miles an hour. And you're going upwards for, it's a 10,000 foot tall building or something. So it's going to take you a while to get up to the top. When you wake up in the elevator is already moving. Are you able to figure out whether or not you're moving from inside the elevator?
Well, you're going to notice that if you notice that you're from stable ground, you're going to notice that.
Well, no, you're just in an elevator, right?
My question
is, are you able to tell whether or not you're moving?
You eventually would, yeah. After time,
well, no, I'm saying right when you wake, right when you wake up, you're in this box. You don't know where you are. It's just a box.
Let me ask you a simple
Are you able to tell whether or not you're moving?
Let me ask you: if you put a scale on the elevator, what would your weight be?
So you can have a scale in your elevator if you want.
If you're going up, how much would you weigh?
You tell me. Do you think that the scale will read a different number than what it normally would read if you were standing on the ground?
I'm just a guy that barely graduated high school. I don't know anything.
So it turns out the answer is and you can actually test this on an elevator. It will read the exact same number.
Okay, so what happens when you're in free fall?
When you're in free fall, it'll read 0. The scale.
Yeah.
But so I really need an answer to this. This is really important to make sure that we're talking about the same thing.
If you're saying the ground,
while you're in this elevator, which again, you don't know, like you just woke up in here, you don't know if it's moving or not. What could you do to figure out if it's moving?
Well, you would basically know that. I mean, you're basically saying that if you're in an elevator, if I can know if you're in free fall and you're dropping,
you're not in free fall. You're in an elevator.
But here's the thing. That's the problem.
The elevator is moving upwards at 10 miles per hour.
I get what you're saying.
So how would you figure out that you're moving?
Fine.
What would you do?
Fine. But how do you tell us that the astronauts are floating in space?
Can you please answer my question? I don't know why you're avoiding it so much.
Okay.
In this scenario, how would you figure out that you're moving?
You would have to know what stable ground feels like. You would have the right.
I mean, you look you're a normal person. You're a normal person. You lived on the ground for most of your life, and now you wake up in this elevator. How do you tell if the elevator's moving?
Now, if you're saying that he can bring the right instrumentation and
what instrumentation would he bring?
Then he would be able to figure that out at some point, right?
Like what? What would he use?
Altitude readers. He would be able to figure that out, how high his altitude is.
How do altitude readers work?
I'm not going to get into that. He can figure out his G-forces. He can figure out a lot of different things.
Well, there's no G-forces. You're moving at a constant speed.
There's no windows and I have no head, or I'm just walking.
No. There's no windows. You can have whatever instrument you want in there, but you can't use any instrument that communicates with the outside world. That's the only rule.
But that's the problem. You're isolating the system for this test, but when we know...
So I'm asking, given that you're isolated, is there anything that you can do from inside the elevator?
And I don't know what's going on, and I'm handicapped?
Look, you just woke up in here. You know who you are, you have all of your past memories, but you just woke up in here. You just don't know if it's moving or not. This is how we do experiments. We isolate variables, right? So I'm asking you, is there an experiment that you can do to figure out that you're moving? Which experiment could you do?
We have technical measurement systems.
Like what?
I just told you. I just gave you one example. I just gave you one.
A G-force meter will not show you whether or not you're moving or not. In fact, it'll read 0.
Sir, I said you can figure out your altitude.
How would your altitude tell you? How would you figure out your altitude? Because the air pressure is the same in your elevator. It's completely sealed.
what I'm
the air
saying
pressure's
is
not
that
changing as your altitude changes.
You could put it on the outside of the elevator if you like.
You can't go outside the elevator. The elevator's sealed.
What? I understand that. I get your cat box experiment.
So it sounds like from
experiment.
the inside of the elevator you can't figure out that you're moving.
You can.
So what if you can? Then tell me how you would do it.
It may not. Okay, here's what I'm going to give you. In linear motion.
Use your noodle.
Okay, fine. Okay, you can't figure it out. But that's not my point.
We agree. I'm glad we agree.
My point is free fall. Explain free fall to me, sir.
So free fall is a kind of linear motion. It's a sort of a generalization of linear motion. I can go into that if you want, but it's a kind of linear motion. And so free fall is just the kind of linear motion where there is where there's nothing but gravity acting on you, right? And I call it linear motion because it's linear in a technical sense in relativity. It's not linear in the sense that you can be in orbit and still be in free fall, and that's technically linear motion through a curved spacetime. It's neither here nor there. But the point is free fall is what you experience when there's just gravity acting on you. That's all it is.
But all I'm trying to just explain is when it comes to free fall, we notice that it's not something that you just become a part of.
We notice that we're in free fall. What do you mean?
Well,
like our stomach rises or something, or
yeah, in all practical purposes, yes, we notice what free fall is.
Yeah, we do, and that's just because we can distinguish it from being on the ground. Being on the ground is not free fall. Being in free fall is free fall.
But my whole point is if we're being told that astronauts are floating because of free fall, then we have to assume that the Earth is also in free fall.
The Earth is in free fall. Yeah, that's true.
Exactly.
And
So
we're
then
in
if
free
we
fall with the Earth, but the
Exactly.
Earth's own gravity. So if we consider just the sun's pull on us, then yes, we would be in free fall from the sun. But there's more than just the sun. The Earth has its own gravity, so we are not in free fall because the Earth is there, because we're on the surface of the Earth, and the Earth is preventing us from being in free fall.
Yeah, but but my whole question is, how do you have stable contact with the ground if you're in free fall? How do you walk on the ground and have a stable weight? You cannot do it.
So we are not humans are not in free fall. We're stuck to the surface of the Earth. That prevents us from being in free fall.
So we're not, but that's what I'm saying. You can't have the cake and eat it too. You're saying one
the Earth
thing
is in free fall. The Earth is in free fall. Humans are not.
Exactly. You're having the cake and eat it too, though, sir.
Those two things are not in contradiction.
Yes, they are, because you
What's
can
the
have free
contradiction?
fall on Earth. We can have free fall on Earth, and we can demonstrate this.
Yeah, I mean, sure, you can drop things, but then those things are not in contact with the Earth.
But, sir, you have to have stable ground at the end of the day.
I don't know I don't know what that's addressing.
You cannot walk on solid, stable ground in free fall.
So humans, standing on the Earth are not in free fall.
Well, that's my whole argument. But you're
humans that are
dividing
not on the Earth, humans that are say falling, they are in free fall.
Let me
They
ask you this
stop
question.
being in free fall when they hit the ground.
Okay, but under your model, they say
Again,
that the Earth is
ignoring
actually,
air resistance, of course.
Your model says that the Earth is actually pushing towards you as well. Is that correct?
I mean, there is a force on you pushing up. It's what prevents you from falling through. Yeah.
But the ground is moving up as you're moving down, kind of. Is that kind of
No,
what
the
you
ground
guys-
is not moving up. At least not in any typical reference frame.
Okay, because that's what I was told. I was told that.
Who told you that?
I was told by a couple of people I was debating.
Okay,
that
who
they
told
were
you
saying
that?
the Earth. I don't remember. I was having a debate.
Okay, the Earth is not moving up.
Okay, so the Earth is stable.
I mean, relative to the center of the Earth is obviously not moving. I don't know what you mean by stable. You keep using that word.
Obviously not moving.
Yeah, relative to the center of the Earth. I mean, it's rotating, but it's not moving. Obviously relative to the center of the Earth.
So
Now,
we're
of course, relative to the sun, the Earth is moving. It's going around it, but that's relative to the sun, not relative to the center of the Earth. So the reason why we feel so you know how you ever go to the gym and you have you do a really intense workout and then you wake up the next day and you struggle to lift your arms or you struggle to lift your legs?
Yeah.
Okay. So that feeling, that is the failure to be in free fall, right? Free fall wants your legs to be down wants your legs to be going down. If you want to get out of bed, you have to lift them and you have to fight against being in free fall.
Okay.
And you ever get that feeling like when you stand up and you just feel like you're sagging because you've been standing for so long, like your body feels heavy, like you can feel it in your knees?
Yes.
That's because the ground is applying an upward force on you. So it applies an upward force on your feet apply an upward force on your tibia applies an upward force on your knee, and your knee then is holding, like it has to apply a huge upward force to keep the rest of your body up. And so you'll feel it in your knees, you'll feel it in your joints, because that's the weak points, right? It's because of the ground pushing up on your feet. Your ground pushes up on your feet push up on your legs push up on your torso.
So you're saying the ground is pushing up on my feet then?
Yeah, there's an upward force from the ground. The ground isn't moving, the ground is pushing up on you.
The ground isn't moving, but the ground is pushing up on me. Is this what you're saying?
Yeah, I can explain it if that's not, if you don't understand that.
Let me just make sure, let me say this one more time. The ground is not moving. The ground is not moving, but it's pushing up.
Not moving relative to you if you're standing on it, sure, yeah.
Not moving relative to me.
Yep.
But I'm feeling the force.
Yeah. So like two things can be pushing against each other without them moving relative to each other, right?
Okay.
I mean, like, that makes sense. Like, if I push against a wall, my hand's not moving, but it's still pushing on it.
Well, see, this is the thing. This is a lot of explanation, but when it comes to
I'm trying to explain things to you that you don't understand.
Well, not that I understand it. I don't see it, right?
Well, that's what it means to not understand it, yeah.
Because this correlates back into my bigger argument when it comes to orbital gravity, because you can't demonstrate this. Where in a lab can you demonstrate orbital mechanics of gravity rotating around a bigger mass to a smaller mass? Where does this happen?
Well, we can demonstrate the attractive force, and once you have an attractive force, it's pretty easy to understand why there would be an orbital motion.
Where are the mechanics to it, right?
Where are the mechanics to it? I don't understand that question.
Where in a lab can we demonstrate these gravity mechanics of orbital motion? Where can we demonstrate this? I know you're going to say the Cavendish experiment. Oh, okay, I get it. But that's a rod or a physical connection, trying to demonstrate something that doesn't have a physical connection.
Where's the physical connection between the heavy thing and the light thing in that case?
You're using a rod, right? For the
rod doesn't connect the heavy mass to the light mass.
There's a mechanical connection.
No, there's not. They're literally not touching.
Okay. So you're still using a mechanical object, right?
I don't know what that question means.
Right,
there's like a light mass, and the light mass is like hanging from a string from the ceiling or whatever, via like it's attached to rods and it's hanging from a ceiling. And then the heavy mass is like separate from it, but it's like close.
Okay.
And so then there's a motion there, even though they're not touching each other.
If the Cavendish data is so real, where can you go on a construction site and they use that data for building a building?
Why would they? I don't know what you mean. They use that data. What data would they use on a construction site?
Where's this data important on anything that we do in life, right?
So
we have the let's say you're walking around with a folder.
That data gets us to the fact that mass attracts mass, but that's not particularly relevant when you're building something. All you need is the local gravitational field, and the local gravitational field is the result of mass attracting mass, but it's one specific mass, the Earth, attracting everything else. So you don't really have to know the specific relationship between the mass of the things, because the acceleration that you get, because of the universality of gravitation, the acceleration that you get is going to be the same regardless of how heavy the things that you're using are. So you don't need the Cavendish effect or the Cavendish experiment to build anything.
The Earth would
but you need but the Cavendish experiment still demonstrates the existence of mass attracting mass.
Okay, but what I'm saying is that if we didn't have the Cavendish experiment, we would still be building skyscrapers.
Sure, you don't need. Well, I mean, I don't know if that's true. I feel like the Cavendish experiment is the kind of thing.
They built the pyramids before it.
Well, the pyramids aren't skyscrapers, right?
Well,
the pyramids aren't
skyscrapers. But they're advanced, aren't they?
The pyramids? Not really. Building like a pyramid is basically a pile of stone.
Okay, but what I'm saying is, when it comes to the actual mechanical demonstration of orbital gravity, we just don't see it. I mean, even when
the Cavendish experiment doesn't. That should be sufficient for anybody who's able to use their noodle.
One thing is, look, even when we look at
it's the thing that you're asking for
to the ground. Even when we look at a vacuum, right? You guys say that the heavier object falls at the same speed as a feather in a vacuum, right?
Mm-hmm.
If we're supposed to assume mutual attraction with gravity, why do we not see any difference between the heavier object hitting the ground faster than the lighter object?
Yeah, so strength of gravity on a heavier thing is greater, but the amount of force required to accelerate a heavier thing is proportionally greater as well. Like, and you know this is obviously true, Morpheus. If you try to push a small rock, it's easier than trying to push a heavy rock, even if you're on ice, right?
But why does it hit the ground at the same
so it
speed as
takes
a feather?
it takes more effort, takes more force to get something moving if it's heavier. And yet, because the gravitational pull gets bigger for is bigger for heavier things than it is for lighter things, those two effects exactly cancel out and so they fall at the same rate.
But you can't. I mean, you're canceling out what? They're hitting the ground at the
mass,
same
the effects of mass.
But
the effects
it
of the
doesn't
mass
matter.
of the thing falling.
There's no falsification of any of this stuff.
Sure,
You're
there
saying
is. You could run an experiment where you try to measure mass attracting mass, and if it came back giving you like, oh, the relationship doesn't go as the inverse of the distance squared, or the relationship is not proportional to the product of their masses, that would be a great falsification of this.
But if they're hitting ultimately the ground at the same speed, right? And you're saying
in fact, if they didn't hit ground at the ground at the same speed in a vacuum, that would be a falsification of the Newtonian gravity.
No.
What do you
it
mean,
would be the
no?
opposite, because I'm saying we're told that planets are attracted to each other in space because of their gravity.
Mm-hmm.
So why am I being told that a heavier object on Earth hits the ground as a feather or something lighter? That's not supposed to happen.
Why isn't that supposed to happen?
Because mass, we're supposed to have mutual attraction for mass.
Yeah,
mass
so the
is
heavy.
supposed to be
You're right. So
hitting
the heavier
ground.
thing. Yeah. So wait, are you saying that the heavier thing is supposed to pull the Earth up?
No,
Is
the
that your
heavier thing should
complaint?
hit the ground faster than the lighter thing.
So it has
They
the
should
heavier
hit the-
thing. The heavier thing has more gravitational force acting on it, but it also is heavier, so it takes more force to get it moving.
But again, in orbital mechanics, we're told that gravity makes gravity masses attract to each other.
Yes.
That's what we're told.
Yes, heavier
we're
things,
not-
more massive things, experience more gravitational force. I agree.
But we don't see that on any
We do
experiments
see
on
that.
Earth. Not
we
with
do
things
see
dropping.
that. So,
Not with things dropping.
do you understand that force and acceleration are different?
I understand that, but it
Okay,
doesn't
so
matter.
hold on. So just because the forces are different, so the force on the gravitational force on a feather is different from the gravitational force on a bowling ball. I agree. You agree with that?
The gravitational force
On a bowling ball is different from the gravitational
your
force
assumption,
on a
not
feather.
mine. No,
okay,
there's just different
on
weights.
my model, do you understand that that's what my model says?
Yeah, that's what your model
Okay.
says. Yes.
Now, do you also understand that even if the forces are different, the accelerations could still be the same? The rate at which it falls could still be the same. Do you understand that those two things are not the same thing?
I understand.
Okay,
that.
so
On
it's
the
true.
model,
The
that's
bowling ball
being-
does have a greater gravitational force acting on it, but it's also true that the bowling ball falls at the same rate as the feather because the bowling ball takes more force to accelerate the same amount because it's heavier.
Okay, so where
There's
do we
two
see,
competing
so where,
effects.
Where in this race do we see any separation? Let me
The
ask you
point
this
is there
question.
is no separation because the mass that appears in the force term also appears in the acceleration term. And so if you have something that's twice as heavy, has twice as much mass, then it's going to have twice as much gravity on it. But it's also going to take twice as much force to do the same amount of acceleration. So, like think of it this way: like you have the same engine. If you take an engine and you put it in a Prius as opposed to a semi-truck, that engine will be able to accelerate a Prius much faster than it'll be able to accelerate a
So
semi-truck.
you're saying that there's a delay in acceleration? Is that what you're saying?
No, I'm not saying that there's a delay in acceleration.
Well, you said there was
The amount of acceleration is the amount of acceleration for a given. So if you fix the amount of force that you're applying to something, if you increase the mass, the amount of acceleration for the heavier thing will go down. If you increase the mass, the acceleration goes down if the amount of force stays the same.
Okay, that's fine. I'll accept that, but that doesn't explain orbital gravity, though, sir.
I don't see how your confusion about a feather and a bowling ball is related to orbital gravity.
If one planet is attracted to another in space, that's because one is pulling down the other.
Well,
right?
they're both pulling each other.
Yeah, but there's a mutual attraction, so one should be closer than the other. Would you not agree?
One should be closer than the other compared to what?
If the mass is bigger than the other mass, there should be an attraction
Yeah, they attract each other, so the distance between them will get smaller with time. Or if they're moving, they might orbit each other or whatever.
But what I'm saying ultimately is it's going to be closer to the object at the end of the day. However,
what's going to be closer to the object?
The heavier object and the lighter object are going to attract closer to each other at the end of the day.
Yeah, unless they're moving relative to each other, then they could be orbiting rather than just falling.
But we know there's a difference because of the weight. That's what I'm saying. They're attracted because of the weight. We don't
look.
The orbiting attraction.
Orbital motion is the same kind. Well, it's not the same kind, but orbital motion arises for the same reason that falling motion happens. They're the same. They're governed by the same phenomenon. It's the same math.
Okay. Well, like I said, I'm just saying that when you do basic common sense experiments, mechanically none of this adds up. It just doesn't. I mean, ultimately,
basic common sense experiments involve isolating variables, involves taking precision measurements. These are the kinds of experiments that scientists do. Now, if you want to be if you want to remain ignorant and do loosey-goosey experiments and not actually control for variables and not actually account for systematic error and not actually take precision data. If you want to do that, that's fine, but you'll never come to a true understanding of the way the world works.
So what would one? Okay, so let me ask you this: let's say you walked into a construction team and they were building the next tallest building in the world. According to your gravity models, what would they take seriously from you right now?
All they need to know, and I mean to be clear, the construction team isn't really the one that's doing any of this.
The engineers, right? Designing.
The engineers who design it, they need to take into account the gravitational force downward of the things that they're using in their building supply.
They know things fall down.
Well, no, they need to take into account the specific magnitude of the gravitational force, not just that things fall. They need to know how strong gravity is.
Okay, and how would that affect the building?
Well, so for example, if gravity were stronger, then they would need stronger building materials. If gravity is weaker, they wouldn't need as strong building materials. So again, for example, like if you have a in a skyscraper, do you know what a counterbalance does?
In a
skyscraper.
No,
a counterbalance.
Go ahead and explain.
Okay, so you know how like the higher up you go, the winds get faster. So a counterbalance, like if you didn't have a counterbalance, it's a force dampener. If you didn't have one of these things in a skyscraper, the skyscraper would just wobble because of the wind, basically, and it would also be a lot more susceptible to earthquakes. So what they do is they hang basically a really huge heavy thing from the top, and it basically just it is something that basically swings in the opposite direction as the wind would be blowing to basically prevent the building from destabilizing. Now, the important point is that you have a heavy thing. You need to know the strength of gravity to know how strong your wire or your cable or whatever it is that's holding the thing up. You need to know how strong gravity is to know how thick your cable needs to be. If your gravity is weak, then you would need a less thick cable. If your gravity is really strong, then you need a really thick cable. And so they need to know the specific strength of gravity.
Well, that's just a material constraint for the most part.
Yeah, the strength of gravity constrains the material properties that they have to use when building a building, or when designing a building, rather.
Ultimately, what I'm getting to, if I went to a builder and they said, and they were building a high rise in California, and I told them there was earthquakes, they would say, yes, we exactly know what that is. We build the building design based
I just gave you an example. I don't know why you're deflecting.
You cannot go there and tell them because of rotation, you have to build this building this way.
Wait, I thought we were talking about gravity, not rotation. Why are you deflecting?
We're talking about building in general. But what I'm saying is
that... Okay, so do we agree that they do have to take into account gravity when building?
No, gravity is just a construct that you guys made up, right?
They have to take into account the force of gravity, which results in downward acceleration of 9.81-ish meters per second squared. They have to take that into account.
This is what the Egyptians had to do. I'll tell you what the Egyptians
do you think that they don't have to take into account the 9.81 meters per second squared downwards?
They had whatever time they wanted to. They knew things hit the ground. They verified that.
No, I'm talking about like engineers when they're building when they're designing a building. Do they have to take into account the 9.81 meters per second squared downward acceleration due to gravity? They don't. They do have to take that into account.
It's just the due to gravity is where I have a problem with.
Well, yeah, I mean, this is a real phenomenon. There is this universal downward acceleration. That downward acceleration is explained by gravity.
But the problem it doesn't work on a ball because you guys throw that on a vector.
It does work on a ball.
No,
yeah.
you guys have vector gravity where you have it
Yeah,
upside
all forces
down
are vectors.
and backwards and
You know that all
these
forces
other-
are You know that all forces are vectors.
all 360. So a ball.
You know that all forces are
gravity
vectors,
going
right?
one direction downwards. Is it going upward on the other direction?
So downwards is
know-
towards the center, so it's going downwards in
but I
all
mean-
directions.
Oh, that's great. But what I'm saying is,
It seems like you're kind of like deflecting
engineers
now away from the
would
original
have
conversation.
To design for that, though, sir. They would have to design for that.
Design for
There's
what?
no design for their blueprints for vector gravity going different directions.
Of course it is. Absolutely. Literally every. So let me show you something. I'm gonna show you something
just
that
go
might
with
be
a plumb
instructive
line.
here.
That's it.
Let me show you
Plumb
something.
line going straight down.
Let me pull something up for you, so then you can see what I'm talking about. I want this file, and I want.
Can I ask you a
think
question?
it's yeah. After I'm done showing you this thing, okay? Is that fair? I just want to make sure I find the right thing. Is it this one? No. Is it this one? No. Is it this one? Sorry, I'm looking through a bunch of files and I just have to find the right one. Okay. Yeah, it's this one. So, let me pull it up.
Some guy said I'm a paid fake flat earther. That's funny.
Well, who knows? Who knows these days, right? Okay, so this is a homework assignment that engineering students had to solve, right? I used to teach engineering students at universities, and this was one of the homework problems that I would assign them. I would assign that it'd be a little bit more than halfway through the very first course that engineering students take in physics. Now, importantly, this particular problem is it's basically the problem of designing a crane, which is the kind of thing an engineer would do. You know, you like figuring out how strong the tension wires have to be, you know, how tough the bolts have to be that are holding the two parts perpendicular to each other. In particular, one of the questions is, what is the magnitude of the tension force on the tension wire, right? That's the kind of thing that an engineer needs to use when solving or when designing a crane. Like they need to know that information. Otherwise, their crane's gonna break.
I'm not arguing with you on that.
Right. So now let me pull something else up for you. I'm gonna pull up the solution set.
I mean, I don't know why we have to go back and forth on basic things. I mean, there's obviously things I'm gonna agree with you.
The trouble is this is, I agree this is basic.
I'm gonna agree with you on
I agree this is
things.
basic, but this is not basic for you. So here's the solution. This is problem 6. Here's the solution. And so notice all those arrows. The red arrow and the blue arrow, the green arrow, the purple arrow. Notice all those arrows? Those are force vectors. So literally, when you're trying to figure out
vectors because of the object or force vectors
because of the configuration of the thing that we're talking about. And noticeably, one of these is the gravitational force vector. It's the one in green right there. The purple one is the tension force vector. This blue one is the force vector downwards from whatever the crane is lifting. The light blue one and the red one are the force vectors coming from the bolts that are holding the crane together. So absolutely, engineers have to take into account force vectors in all sorts of directions from all sorts of different causes, one of which is the gravitational force vector.
Okay.
It's just the reality.
But that's fine. But there's nothing rotating on that, though. If we're supposed to have
rotation has nothing to do with your original claim.
The vectors are straight down.
You keep bringing up
right?
rotation whenever we're talking about force vectors.
Well,
or you brought up rotation in the context of force vectors when we're talking about gravity. No, you could have force vectors even if the Earth wasn't rotating.
Okay, so if you were to build that right on a ball, let's just say a not a ball, but just a model ball, right? And you were to spin that, do you not believe that force would affect whatever you were building?
Yeah. So that, and I can show you exactly what would happen. So what would happen? What would happen in that case is that this force vector would get slightly. Sorry, this force vector would get slightly shorter. So it wouldn't be as long as it is, and this force vector would be slightly shorter. It's the only effect that you would have. Oh, and also this N1 would get slightly shorter as well. That's the only effect that it would have, and in fact, that's built in. That's built into the local gravitational force downwards. Well, so if the Earth was not rotating, in fact, this green one would be slightly longer. This red one would be slightly longer. This blue one would be slightly longer.
But something is moving, though. Is that correct? At the end of the day,
relative to the crane, no.
Relative to the vector of gravity, if you put that model on a ball.
relative to the vector. You don't say that motion is relative to a vector. That's
but what I'm saying, if you put that model on a ball, eventually there would be an effect on that structure if you were to turn that ball around.
I just told you what the effect would be.
It would, but there would be an effect, right?
Yeah, the effect would be the length of those vectors would be slightly different, and that's accounted for when you take your local measurement of the strength of gravity.
You can say slightly different all you want.
Yeah.
What I'm saying,
I can tell you how much different it would be if you want.
Yeah, but this is what I am saying. What I am saying is that you can't have things spinning around and not design for it. That's what I am saying.
Sure, you can.
No, you can't.
Because it turns out the spin is very, very slow. The spin is very, very slow, so the effect is very, very negligible.
That's not a reason, no. Because
it's a great reason. Yeah. So the actual effect is proportional to the angular speed squared times the distance away from the axis of rotation. So the angular speed squared is enormously tiny. Like the Earth's angular rotation rate is remarkably slow. And the distance away from the axis of rotation will of course depend on where you are. In the case, like if you're on the equator, it'll be like 4,000 miles. If you're in Europe, it'll be like 2,000 miles or 2,500 miles or something like this. But
argument is because it's slow, and that's why.
The effect. The effect is there. It's just extremely tiny.
Okay, so is it tiny or slow? We got to lock this down.
Look. So because the Earth's rotation is slow, the effect on the crane is tiny.
Okay, so it's slow and the effect is tiny. But aren't the results build up over time?
No, they don't build up over time, no.
Okay. What I'm saying is this. If you're in a house, right, and it was turning upside down, very, 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 very slow, do you not think we would see effects that would be building up over time, even though it was being done really slow?
If the orientation of the forces were changing over time, relative to the orientation of the crane, for example, I'll just pull up the crane again. So if these forces were rotating relative to the crane, like if the direction of the forces were changing relative to the orientation of the crane over time, then yeah, of course that would accumulate. But the point is the orientation of the forces are staying the same because the crane is attached to the ground.
Yeah, but the Earth rotates 24 hours a day. It rotates upside down.
The crane rotates with it.
Okay, so in one day we're going to have to assume that the crane is somewhere off to one degree or the other, upside down.
Well, that would be 12 hours, not 1 day. And one day it'll be back where it started.
That's what I'm saying.
But in 12 hours, yes. So in 12 hours, in 12 hours, hold on. In 12 hours, this is what it would look like from a northern hemisphere perspectives person, for example. Okay. But you know what? The relative orientation of the forces are all the same. Mm-hmm. So solving these equations, completely identical. Everything is exactly the same.
So when you do that, right? Let's say you put a cup of water on that, right?
Mm-hmm. Yeah. So the force in the water will be pulled in this direction, from this perspective, it's pulled in the upward direction.
Yeah.
The water will be pulled upward to the closed part of the cup in this from this orientation, from this perspective. Yeah.
That's my whole issue. If you put a cup of water on there, it's going to stay stable. The water's not going to
tilt. Yeah, it will. Just like how the crane stays stable, because all of the forces are rotating with the crane.
Yeah, but do you if you got on a ball, right, on a model ball, you could not do this, sir.
Yeah, literally. Okay, look. So the force, we can actually just simulate this, right? We're just going to simulate exactly what you're talking about. So here, notice that the force of gravity is downward. And the force of the load is downward. The two normal forces are up and to the left. The tension force is down and to the right. And so you'll have some system of equations. And by the way, this is the reason why we're talking about equations, is because this is what engineers do to figure out, what material properties they need in order to build their thing in a safe way, right? They have to consider material properties. They have to solve equations to figure out what kinds of materials they need, how thick their cables need to be and all that. So now let's pretend that 6 hours have passed. 6 hours have passed. Well, now the force that was down is now left. The force that was up is now the force that was down is left. The force that was up is right. The force that was down and to the right is now down and to the left. But notably, all of the forces have the same relative orientation to the crane and to each other. So the equations are exactly the same. So regardless of whether or not the system has rotated, the things that the engineers do completely unchanged.
You know, I would love you to talk to a building engineer, and I would love to see.
I literally taught them.
But what I'm trying to
I
explain
literally
is,
taught them. They were my students.
well, here's the thing. I'm saying the Earth isn't moving, right? And you're saying the building.
So the crane, the crane
you.
isn't moving relative to the Earth. The Earth isn't moving relative to the crane.
But you ultimately, you see what's happening here. I'm saying the Earth isn't moving. You're saying the building isn't moving, right? That's pretty much where we're arguing.
No, I'm sorry. You're misunderstanding if that's what you think I'm saying. No.
Well,
the
you're
claim
saying
is
the building
that
is relative to its
the
gravity.
building is not moving relative to the ground.
Okay, but it's
I'm not saying the building isn't moving. I'm saying the building isn't moving relative to the ground.
Okay, but
those are different statements.
You still have
one is a category error, the other is an explicit, an exact statement.
Okay, so how do you mechanically demonstrate this on a model? Let's forget about the drawing.
I just showed you how you can demonstrate it on a model. This is a model.
You're showing me a drawing. I get it.
That's what a model is. I mean, a model is some sort of. A model is a, it's a depiction of the way the world actually is.
I'm talking about a physical model, right?
Okay, you want me to like? Look. You can. So does it have to be something you can hold with your hands in order to understand it? Like, what's the issue?
I mean, you can't. What I'm saying, you can't get a Lego set and spin it around and not have the effects change.
Well, look, the reason why, and I understand the confusion. The reason why it seems like when you spin something on the surface of the Earth that the effects change is because when you spin something, like if you take I don't know, a model of like a Lego model of the Titanic or whatever, when you flip it upside down, the forces, namely the gravitational forces, are not spinning with it. So the forces are changing their equilibrium because the relative angles, the relative orientations are no longer staying the same. And that's because the gravity is still pointing down even as you rotate the Titanic Lego model. But if you took that Titanic Lego model and you brought it to Australia, it would still be stable because the orientation of the forces and the would be, or the direction that the forces are pointing in are still aligned with the orientation of the structure. You've just rotated the whole thing.
Could I ask you a question? Because you keep saying pointing down with gravity, right? You keep saying that.
Yeah.
Now, are you saying that like at a particular 90-degree angle? Is it slanting?
Like when we're standing on Earth, down is like this way?
I understand that, but
okay, just checking.
If we have a clock dial, right? Do we just say the clock dial is straight no matter how we look at it? Like it's going around,
dial?
Right?
Clock dials,
we look at a clock.
They do tend to be straight, yeah.
But as they go up and down the dial, they're not,
up and
there's
down
a
the
slant
dial? You mean like when they go around?
A mechanical clock. We
yeah,
would see
like
that
when they go around.
But you're saying
the hands are still straight the whole time.
Yeah, the hands, yeah. But you're
the hands
saying
are still
that the hands,
straight. They're just changing their angle.
Yeah, they're changing their angle.
But they're still straight.
What I am saying, sir, is that if you put a force like a waterfall on the dial at 1 degree, it's going to have a different effect as it would on another angle. It's not going to be going straight
that's
down.
because we're living on Earth, and Earth has Earth applies a gravitational force.
Yeah, but
so regardless of the orientation of the dial, the gravitational force from the Earth, like the actual Earth, is going to be downward. Regardless, the orientation of the dial is not affecting the gravitational pull. Now, if you're in a different part of the Earth, then the gravitational force will be in a different direction.
But what I'm saying is that if I'll accept your gravity argument, that's fine. Everything goes down to the ground, but it's still not giving me organized containment, right?
Okay, this is a pivot again.
Well, I'm not really pivoting.
You hugely are if you're talking about organized containment. Absolutely, you're pivoting.
What I'm saying is you can't have different vectors of gravity and have the same effect of it, right?
Why not?
So if
why not?
Because the vector is not pointing straight down; it's slanting.
Hold on, let me show you again, and we can. I don't know what the hard part is here, but we're looking again.
You can't drop something straight down slanted, can you?
So look, imagine now that this crane is on the side of the globe Earth, right? It's not the top; it's at the side. Well, gravity is now pointing to the left. That's what the green arrow is. Gravity is pointing to the left. The load force is pointing to the left. The normal force is pointing up and to the right. The tension force is pointing down and to the left. But this crane still works even if it's on the side of the Earth. The side of the Earth, like the, say it's on the equator.
Okay, so you're
this
saying
would
it still works
work.
even if I didn't design it to be that way. You're saying it's still going to work.
Yeah,
even if
because
I
the
didn't design
orientation of the forces and the relative to the orientation of the crane is unchanged.
Okay, so even though I didn't design that building to work that way, it's still going to work.
Yeah.
That doesn't make any sense.
The equations are actually identical.
That means the forces aren't real. If I didn't design
it just means that the equation it just means that it's in equilibrium regardless of how much you rotate it.
But in any practical sense, you would have to design
so what do you think would change? What do you think would change in this? What do you think would need to be changed in order for the crane to work?
I don't know.
When it's on the equator?
But I know I would have to design it to sustain whatever it's being counteracted to. Because that's
what is the change in design that you would need to do here?
Submarine to just relative go down no, you have to build it to get the protect against.
Okay. Let's say that you design the crane to work at the North Pole.
That's like building an accidental submarine.
Let's say that you design the crane. Let's say you design the crane to work at the North Pole. So it's in this configuration, right? Gravity's down, and then all of these other forces are in their relative orientations. And then you pick up the crane and you take it to the equator. So now it's sideways. So what would you have to change in order for the crane to still work?
Well, but the problem, you're saying it's sideways, but you're saying there's no force affecting it. That's my argument.
All of the forces are still there. What do you mean there's no force?
They don't exist.
All the forces are still there.
There is no force because there's nothing. I didn't design that building. There's no counter reaction. I didn't.
What are you talking? What is a counter reaction?
I didn't design that building to be sideways. I did not design that building to be sideways, sir.
Look, everybody is sideways relative to somebody else. This is like
that's not how it works,
sideways
sir.
Sideways is not like a technical term, right? What's important? It's literally not. What's important is what are the forces? Do the forces still allow the crane to do what it has to do? So in this case, the goal of the crane, to be clear,
in this case, are all on paper.
To be clear, in this case, the goal of a crane is to make sure that something on the ground can get lifted up, right? That's the goal of a crane,
sir,
right?
Do we agree on that? Gravity, sir. This is paper gravity.
Okay, so now you're just rejecting it because you don't like that it was drawn.
Well, you're giving me paper gravity, sir.
Okay, that's cool. You can call it paper gravity all you want. So, look, what is the goal of a crane? What is the goal of a crane? Can you tell me what the goal of a crane is?
Sir, it's to pick up objects.
Okay, so there's an object sitting on the ground, like this hash line, that's the ground, right? If we're on the equator, that hash line is the ground. There's an object here. To pick up the object means that it has to be able to sustain a sufficiently strong downward pull at the end of the crane. That's what's happening when a crane is pulling something. The thing pulls down on it, and so like it wants it to tilt over. So you have to design the crane enough so that it doesn't tilt over, right? So there's going to be, in this case, down is to the left, and so here there is going to be a force that is pulling the crane in this direction. On this piece of paper, or in this depiction, it's going to be pulling the crane to the left. Now, there are going to be some other forces involved here. Namely, there is the force that the bolts are holding the crane together with, right? The bolts, connecting the tower of the crane with the arm of the crane, those bolts are holding it together. And so that's what the light blue and the red forces are. You could consider it as one force if you wanted to. I just broke it up into two pieces. Then there's the force towards the center of the Earth. That's what we call gravity. So towards the center of the Earth, well, if the ground is here, then towards the center of the Earth is this direction. And then there's the force of tension in the wire on the back end of the crane. Now, that tension, it's going to be in the direction connecting the arm of the crane to the ground. And so, in the drawing, there's a connection there. I'm just drawing the direction of the force. The tension force will pull that crane arm down into in this case, closer to the ground and a little bit in this direction. So it's down and to the left in this picture. I mean, all of the forces are identical here. And so in this situation, even though it's sideways, it can still lift an object from the ground. It can lift it above the ground. And so it still works perfectly well.
I'm honestly following you, sir. And it all makes sense on paper. I
don't believe you, to be honest.
It does. It does make sense on paper. What I'm saying is that we can't demonstrate this.
No, I agree. It makes sense on paper. Okay. I don't believe you that you're following me.
Even if you put it on a model, it doesn't work. It doesn't work on a model. We don't observe it.
It sure does. You can put this into a computer model, no problem.
Well, what I'm saying is we can't observe this in the reality, right? We can't verify it.
Sure you can. You can
You're
just
saying
build a
that it's
crane
there.
here, and then you can build the exact same crane with the exact same stipulations on the equator, and they'll function identically.
I will tell you, effectively what you're doing is you're trying to tell me that Casper the Ghost exists. You built a really fancy scale, but now that there's no weight measurements, then you're saying, well, that's
There
why
are weight
he
measurements.
exists.
There are weight
That's why
measurements.
Casper the Ghost exists, because there is no weight. That's not how it works.
There is weight here.
That's not how it works. We're measuring ghost here. We're measuring phantom gravity.
Oh,
paper
so
gravity.
wait, so hold on. So now you're telling me that we can measure something? What is it that we're measuring?
No, we're trying. You're giving me ghost
because these are things that you can measure. Oh no,
This is
these
a
are
ghost.
these. There's nothing ghostly about this. You can measure these with force meters. There's literally devices that you can, like, you know, there will be a rope connecting.
Oh, so,
say,
so we can measure a building being upside down then.
Well, so you measure magnitudes of forces with force meters, and what you'll find is that the force meters are unchanged, regardless of whether you're at the North Pole or on the equator, or at the South Pole. Like the force magnitude will be exactly the same, but the direction will be in a different direction because the force meter will be in a different orientation.
Ultimately, the building designers are not building any blueprints for this. Ultimately, at the end of the day,
It turns out that
They don't
regardless
have
of how you rotate a
The math
system,
is so
the
good
equations are
that
the
they don't
exact
even have
same.
the math is so good and gravity's so good that the
Yes.
mechanics they don't even have to build for it.
Well,
Gotcha.
yeah, I mean, if you rotate the whole thing, then nothing's going to be different about it. Of course.
The math works. Okay, well, there you go. Well, there you go.
Yeah,
Tell your
of
audience, it works so well.
I mean,
that
no,
you don't even have
like
to
the
use,
equations
you
are
don't have to
invariant
use-
under rotation, right? So.
Man,
like
we know how this.
that's just part of like
That's like
because you're in
being
a
on a
spherically
roller
symmetric
coaster.
system, the equations are invariant under rotation. So.
Man, you have to design for forces, man. You would be a bad roller coaster designer. I would tell you that. Do not design roller coasters.
The people who
please.
design roller coasters are the people who took my class.
Oh my God! Please tell me.
Yeah,
I
I
do
taught
not
hundreds of
wanna
them.
Okay, because apparently to you're not supposed to take into account your phantom forces. So
Nope,
I
no
guess it
phantom
is what
forces
it
to be
is.
found. I mean, you can keep
Well-
straw manning the position if you want, but it just makes you look worse.
But it's not. It's not. I'm just trying to be real with you, man. I mean, ultimately,
I mean,
at the end of the day,
look,
we
I
have
understand
to,
you're trying to
look,
be real. You
I'm
just
not-
don't understand what's
I
going
don't-
on here, and I get that. Like, if you wanted to, I could send you my lecture notes so that you could learn it too, because it's pretty clear that like these are just things that you don't have the. I mean, like you seem like a normal guy, so I think that you could probably learn this stuff. You just don't know it, so like of course it's gonna seem like magic to you, right?
Yeah, well, you could say
Like
that.
I can send
mean,
you the lecture notes if you want.
But the problem is that the logic just doesn't pan out. You just the logic, the
Well, of course you
mechanical
would say that
logic
because
doesn't
you're.
pan out.
Of course you would say that because you don't understand it.
Well, I understand what I need to know. I mean, even look, even
apparently
with your
not.
moon and sun, that doesn't even make any sense. The sun has a stronger orbit around the moon.
Of course, that's what you would say.
But I don't want to go off track. This what I'm saying is this, guys.
So, like, by the way, this is like the first set of lecture notes, and in fact, actually, just so you guys know, I can actually show you. There's a YouTube series where you can go watch my lectures for an entire college quarter on these topics. So, let me show you the account, and you could go watch too, Morpheus, if you want. So here, here's the account. It's not. Like I haven't broadcast it because I'm not sure if I'm legally allowed to, because even though they're my lectures, they were done while I was an employee at the university. But like the account is just, if you search physics lectures 9A, the account is physics lectures 4649. There are lectures for literally an entire year's worth of physics courses at a college level. You can go watch them if you want. Start with 9A, that's the first quarter. Then you go to 9B, then 9C. Like if you want to watch this, here's the first lecture. There's the second. Goes all the way up through lecture, what? 24,
that's my whole thing. I'm gonna let you get to
25?
some other
No, it
guests.
goes to lecture 27, in fact. So you can go watch these, and then you might understand what we're talking about. But at this point, it's fairly evident to me that like these are just things that you don't know. And so it seems weird that you're trying to like say that they're like, fake when it like just from look. Imagine telling a heart surgeon like, you're just talking about phantom valves and phantom pumps. Those aren't real. Those are just made up phantom made up phantom mechanisms in the heart. They're not real, and like obviously they are real, but you wouldn't know that because you're not a heart surgeon.
I'm not a heart surgeon, but I do know that they have to examine that with the physical reality that which they're in.
Yeah, all of these things that I'm talking about have been examined in physical reality. Yeah.
Well, again, all I would say is that if I were to study blueprints of buildings, there's not going to be any verification on gravity forces or rotation or anything.
You will see. You will absolutely see forces due to gravity on there. You absolutely will.
There's none. There's none.
Oh, okay. So to be clear, when you see statics diagrams like the one I showed you, there's no gravity. Because those diagrams are the kinds of things that go into designing buildings.
If I go to a building firm, they're gonna laugh me out of the building if I start talking about rotation, and we have to design for that. They're gonna laugh me out of.
You don't have to design for it. That's the lovely part. Because the rotation is negligible, so you don't have to design for it. But that's a cool straw man of my position. My position was never you have to design for rotation. You don't have to because it's negligible.
Exactly. It's not moving. Negligible.
No, it is moving. It's just negligible. If you want to detect, if you want to detect the rotation, you can. You just have to design experiments specifically to see whether or not it is. On an everyday basis, you're just not sensitive enough to those small effects.
If we both walked in there trying to convince these people of rotation, they're going to laugh us both out of the room.
So I can guarantee you that 99% of engineers think the Earth is rotating.
They're gonna laugh you out of the room if you tell them to design based off of that.
I would never tell them to do that, and that's a straw man of my position.
I know you wouldn't.
It's not necessary because it's negligible.
It's paper gravity. It's paper. It's just paper mechanics, sir.
So gravity again. Gravity is not related to rotation, but you seem like you're kind of stuck.
It's still, no, gravity does have an effect on it because there's rotation.
Gravity and rotation are not related here. The rotation of the Earth is not. The rotation of the Earth is not related to the gravity. No.
But we're talking about Earth, aren't we?
Are you sure we're talking about Earth?
We can't separate one to the other.
Yeah, you can.
They're all interconnected, aren't they?
No, they're not interconnected.
Oh, okay. So we got to separate them. Okay.
Well, you can separate them.
Yeah, but in reality, they work all at once, don't they?
Yeah, but they're separate effects.
Okay. They're separate effects, but they all okay. All right.
They're separate phenomena.
Right.
Yep.
Yeah, talk to some more building designers. Let's find out if they design for rotation because I'm at the end.
Why are you straw manning me, Morpheus? You were being so good faith the whole time, and now you're straw manning me.
If they can tell
I literally never said, and I've never made this claim that building designers have to design for rotation. I literally never made that claim. So I don't know why you're bringing that up as if I said that.
Well, I'm not saying you said that. I'm saying.
So then why are you bringing it up? I never made the claim. In fact, I agree with you. I agree with you that building designers would not have to account for the rotation of the Earth when they're designing their buildings because it's a small effect. It's negligible.
Okay, it's negligible. I'm saying there's none. You're saying it's negligible.
Yeah.
Okay.
And now the thing is if you want to figure out which one of those is true, whether it's negligible or whether it's none, you have to design an experiment to test for it. And you can do that. And this has been done. These are called, a good example of this is called a Compton generator. A Compton generator is it's an experimental test that you can design and build. It's a physical object, and it will measure either the presence of rotation or the lack of rotation.
All I'm saying is this.
You're not going to address anything I just said, will you?
No, I just listened to you. Take that data.
Okay, so
take it to anybody in the real world and see if they act on it. That's all I'm saying. I'm not an expert in any of this stuff. See if they act on it. Yes.
Whether or not people act on it doesn't mean that it's not real.
When they're doing construction or any kind of
you don't have to act on it when you're building a building because it's negligible. It's a small effect.
Okay.
Well, I don't know why you're so confused on this. The claim is that the effect is small, so you don't have to account for it when you're building a building or when you're designing a building, but the effect is there and it's measurable when you design precision experiments to try to see whether or not it's present.
Bottom line, we're on solid ground, sir.
Of course we're on solid ground, and that solid ground is rotating with respect to the center of the Earth.
It's not moving. It's not moving.
It is, relative to the center of the Earth, it is.
No, because you could point to a star and say, well, we're going 5 million miles per hour because I pointed to the star here. That don't mean SHIT, bro.
I don't see what that has to do with anything that I've said.
Anywhere in the sky and say we're moving.
Checkmate, Glober. You can't think that the Earth is moving through the sky at 2 million miles per hour. That's absurd. Okay, that's what you're doing right now.
Hey,
it seems like you don't understand relative motion, so I'm not too worried.
And say we're going this speed or that speed, but ultimately
relative to it, sure.
The ground ain't moving.
Relative to what? It's not moving relative to what?
I'm sitting here in a chair right now. I'm not moving.
Yeah, you are. I bet you are.
I'm not moving.
Relative to what? Relative to what?
I'm relative to this earth. I'm not moving.
Yeah, relative to the earth. Of course you're not moving.
Now we could talk about heaven.
Relative to the ground. Of course you're not moving. You're sitting on the ground.
Maybe your heaven is your star system.
Wait, so do you understand that? Do you understand that? Do you understand what I just said? Do you understand what I just said?
What is it?
Oh, you don't even have you even been listening to anything I've been saying? So of course you're not moving relative to the ground.
This is the same conversation we've been having for a whole 30 minutes. This is what I'm saying.
You understand that nobody's making the claim that you're moving relative to the ground when you're sitting in a chair, unless the chair is like rolling around, of course.
But the problem is, your heaven or your space, we have to believe in that.
That's a really cool straw man. That's an awesome straw man. I love you straw manning my position like that. It's super appreciated. I love the good faith conversation that you're doing. No, fortunately, we can provide evidence. You don't just have to believe me. I gave you an example of the kind of experiment that you could conduct yourself. Well, I'm sorry, do you just not like evidence? Are you just not an evidence fan? Like, I get it. I get it. If you're not a fan of evidence, if you would just rather believe whatever some TikToker or YouTuber told you, then, like, I get it. Like, maybe the globe Earth just isn't for you because, like, you're just not into that kind of thing. I'm an evidence guy. Like, I like to believe the true thing about the world. So if I'm not sure, I just go out and look at the experimental data, and then I come to the conclusions based on that experimental data. But if that's not for you, that's not for you. I get it.
You guys don't even have a definition of what a straight line is, okay? So how about you get
Sure I do. It's the covariant. A line is straight when the covariant derivative along the path of the path or of the tangent vector of that path is 0. That's what it means to be straight.
There you go. But what I'm saying,
there you go. You didn't understand a word I just said, did you, Morpheus? Nope, that is the definition.
And I don't care to.
I know you don't. You don't care to understand how the world works. I get it.
I'm sitting in a chair right now. You need to convince me I'm moving out of it.
Nobody's making the claim that you're moving out of it.
You haven't done it.
Literally, that's a cool straw man again, I guess. Nobody's making that claim.
Well, I'm claiming that I'm sitting here not moving.
Yeah, you're not moving relative to the ground. You're moving relative to the sun. You're moving relative to Mars.
What you say. I'm not moving. I'm not moving.
You're not moving relative to what?
And when I build my building...
What are you not moving relative to?
When I build my building, we're building...
What are you not moving relative to?
I'm relative to the Earth. That's all I care about.
Relative to the surface of the Earth, yeah, of course you're not moving.
What Jupiter's doing. I don't care about...
Right, but are you moving relative to Jupiter?
I don't care about a star system 50 trillion miles away.
Why aren't you answering my question? Are you moving relative to Jupiter?
I'm moving relative to... I'm not moving relative to Earth. I'm sitting here.
Well, that wasn't my question. My question was, are you moving relative to Jupiter? Jupiter's the thing that you can see in the sky, right? You can see Jupiter in the sky.
Can I?
Yeah, with your eyeballs.
I hope so.
I would hope so too. So are you moving relative to Jupiter?
I'm moving stable to the ground that I'm sitting on. I'm sitting in a chair right now.
Why aren't you answering my question? Are you moving relative to Jupiter?
I'm sitting in a chair, sir.
I understand that. Are you moving relative to Jupiter?
Let me use my imagination. Let me think about this. Hold on. Let me think about Jupiter. Hold on.
You don't have to use your imagination. This is not an imagination scenario.
Hold on.
Jupiter is a thing that you can see.
Hold on. Jupiter must be moving, so therefore I must. Hold on. I'm thinking. Okay, you're right. Yeah,
this is for the first time in your life.
I'm moving.
Relative to.
I thought about it.
You're moving relative to. What are you moving relative to?
It's my imagination.
What are you moving relative to?
My imagination tells me I'm moving because
relative to what? Relative to what?
Relative to Jupiter.
Because I'm imagining. Congrats! I'm glad that we got there, Morpheus. I'm so proud of you.
Yeah, I thought about it. Well,
I'm so proud of you for using your brain. It's so brave, Morpheus. You're so brave. I'm so proud. That's got to be a first for him. I understand that it was hard. All right, let's read some super chats and then move on to our next guest. What a time to be alive. Imagine sharing an Earth with Morpheus. What a time to be alive. From Curtis Martin with the $5. How do you recommend a broke guy in North Dakota get into a STEM program? I'm 29, just really wanting to do something useful with my life. Please help. The thing is unless you're extraordinary, the odds of getting a full ride scholarship into a university is quite small. That's the reality, because basically everybody tries to go to universities these days, which is, I think, it's generally a good thing. But that means that there's only so much that they can give out for scholarship. So what I would suggest that you do is I suggest that you, it's going to cost you some money, so you'll need a job, of course, but save up and try to go to a community college, whatever your local community college is. Save up and take 2 years of you can get like a general, like you can get an associate's degree in like general science or something like that, And that will let you know whether or not it's worth taking out loans to go get a STEM degree, like a STEM degree at a university, like after you get your associates. From Icy Spin with the $2, but Flat Earth is easy. Stop explaining stuff. It's too much. I know it's easy for them. That's the unfortunate thing. It's so easy that they just don't want things explained. Yeah, or marry a rich girl, I guess. Or a rich man. I don't judge. From Nick with the $2, good thing he's not a crane engineer. Yeah, right? I'm actually not sure what he is, but I'm glad he's not a crane engineer. From Zetal, from Zeta Alpha Kappa. This guy with the $5, this guy melts if you ask him why things fall, or under his model, what is the exact mechanism which causes things to tend towards Earth? Oh, he'll just say, oh, I don't have a model. From Mr. Delightful Song with the 2,500 CLP. Now, CLP is Chilean. What is CLP? CLP is Chilean pesos, that's right. Chilean pesos, 2,500 Chilean pesos, very much appreciated. Tell him that gravity always points to the center of mass, not a static down. Yeah, I tried. From Icy Spin with the $2, how many clips is yellow color good for? One long one, but it'll be good. From Von Doodle with the £2, the only force acting on this collar is obtuse. That's a good pun. It's the force is at an obtuse angle. From the Rabbit Squirrel Sage with the $5, you don't have to design a building for Jupiter's gravity. Conclusion, Jupiter doesn't exist. True, or gravity doesn't exist. Have you thought about that? From Empiricist with the $2, I'm a big fan of evidence too. Yeah, right? Like, it's really important to me, but if it's not important to him, I get it. From Zeta Alpha Kappa with the $2, force of gravity on 1 kilogram is 9.81 newtons. Force of centrifugal on 1 kilogram is 0.03 newtons. Yeah, so it's less than half a percent. And from Dr. Fudge with the $10, he's just reverted to actual toddler status, literal oppositional defiance. You know, maybe there's an oppositional defiance thing going on here too. From Enough Data with the $2, is cringe linear, exponential, or logarithmic? I think that there's like I suspect it's logarithmic. I don't think that you can cringe linearly or exponentially. That'd be too much cringe. All right, let us bring up our next guest. I just want to close out of some of these things, or minimize them anyway. Making sure that there are no guests on Discord. Let's bring up Caleb Steimel. Caleb Steimel, how's it going?
Hello. Good, how are you? Why that music? Oh my.
What? You good?
Yeah, I'm good, sorry.
What shape do you think the Earth is, Caleb?
It's flat.
Okay, why do you think so?
Well, the main reason is because I took a 14-hour flight from California to South Korea when I was in the military. And I was thinking about it recently, and I realized there was no angle. It was just like a straight flat across. Like, maybe the Earth is too big. I don't know, but I don't think that the math adds up for that. It's like 14 hours times 600 miles an hour, and I still can't see the curvature of the Earth. How fast do you have to be going to see the curvature?
I don't understand how speed would help you see curvature. It seems like you just have to be sufficiently far away. Yeah.
Okay, but I don't know. It's tough because you can't trust videos because they can be like fixed. Because I've seen a video of like a balloon going up and it looked like the Earth was round, but then they also have pictures of the Earth, and they also have movies that where you can see the Earth. So if they can make a picture of Earth in a movie, then it shouldn't be that hard to fix it. So that doesn't convince me. Okay, let's move on. So my next
Wait,
argument
just to be clear, like, what would be the motivation for like some random guy on YouTube who's not like affiliated with Hollywood or the government or whatever? What would be his motivation for faking this?
Well, I think the whole paradigm is that they had to maintain control.
But this is just some random YouTuber. It's not like a guy associated with like the Freemasons or whatever. Like, it's just some random guy on YouTube.
Well,
he doesn't even have a lot of subscribers. Like, he's just a dude. Why would he be motivated to fake this?
Well, you might just be like spewing, like you might just be what's the word I'm looking for? Like basically fall into their bullshit, basically.
So, but look. So, hear me out. Suppose that I'm talking about a guy who launched his own rocket. It's really impressive. He built the rocket. He launched his own rocket. It's like think of it like a souped up model rocket, you know? It's not like a big NASA rocket, but it's like a souped up model rocket. So he launched his own rocket and he gets to basically to the edge of space. He has cameras on it. So if he was tricked into believing it the whole time, right? Like, you know, he was indoctrinated growing up or whatever. And then the rocket comes down, he gets the video and he's like, it's flat? Why would, if he was indoctrinated and then he sees it for himself, why would he then go into Photoshop and then manually edit, or, you know, whatever, Adobe After Effects or whatever it is, and then manually edit everything to fake the thing that he just saw with his own eyes? What would be his motivation?
Well, to be honest, I haven't really seen a lot of videos on
I can show
YouTube
you.
of people sending rockets up.
Want me to show you?
Okay.
I have one right here.
Well, the government could have come in and doctored that.
This is just a guy.
The
government, it's on YouTube. It's just a guy.
They have they have all kinds of surveillance, and the three-letter.
It's just a dude.
I know. Okay.
What's
it sounds like you're trying to convince
what's
me
his
by
motivation?
It's the government that's controlling everything.
But the government, so the government he's not associated with the government. He's just like a guy.
Well, I mean, we don't know what happened in the background. I mean, maybe the government, when he got the camera, maybe the government showed up when they saw it go up, and they could have threatened him or threatened his family and been like, oh, if you don't.
Okay, but now you're making a whole bunch of claims, and those claims you would have to provide evidence for those claims that this happened.
Well, I can't provide evidence for everything.
So then why would you think it happened?
Even science doesn't understand everything.
Why would you think that happened then?
Well, like I said, because the government has to maintain control. I mean, think about it, the founding fathers.
But the government. So that would only happen if the Earth was actually flat, and you're trying to dismiss this evidence as the Earth not being flat. By the way, this is the rock. This is a still from the rocket being at almost the edge of space, which is 300,000 feet up, and you can see that it's pretty obviously curved, right?
Yeah, but I mean, videos can be doctored, so.
Oh, right, but there's no evidence that it has been doctored.
And
well, why would this guy
doctor it? I don't have access to the original video.
Why would this guy doctor it unless he was also in on the conspiracy? Why wouldn't he just post it? If it was real, why wouldn't he just post it? Or sorry, if the Earth was actually flat, why wouldn't he just post that the Earth is flat? You can't use that there is a giant conspiracy theory to justify that you can't use the fact that there is a giant conspiracy to try to justify that there's a giant conspiracy. That's circular. You need some sort of external piece of evidence to justify the claim.
Well, let me think for a second. I mean, I'm not all powerful. I'm not in a position of power where I can fight against the government that way. I don't have that kind of evidence. So I can't prove it.
So why would you believe it? Then why do you believe it?
It's possible. Because I was on that plane ride, and because.
Okay, but what about the plane ride convinced you? Look, I've been on the plane ride. I've been on a long plane ride too. I don't see how that would. I don't see how that would make you think that the Earth is flat.
Yeah, but I mean, that's your position. So of course you're gonna say that.
What's my position?
What I mean? Your position is that the Earth is round because you're a scientist.
Yeah. So my position is that the Earth is round, not because I'm a scientist, but because I've thought critically about the data that's available.
Okay. All right.
Which is what you should do, right?
Well, it's not always that simple, because
you shouldn't think critically about the data.
Well, if you have a powerful government that's doctoring everything,
the data doesn't come from the government. The data predates the government.
So they made it up to make it make sense.
The data predates the government.
Okay, there are certain things that could make sense for round Earth, but it could also make sense for flat Earth too.
Can you explain? Okay, so let me give you an example of something that doesn't make sense on a flat Earth at all to me.
Okay, that's right.
Have you ever seen a sunset, a sunset when it's cloudy?
Yes.
Okay. Just for those who haven't, there's a lovely picture that I want to pull up really quick. If I can find it here. I think it's here. Sunset cloudy. There's a particular picture that I'm looking for, which is really, really nice. It's this one. Here it is.
Are you talking about what's it called? Where it goes, it turns smaller as it gets.
No, that's not what I'm talking about. I'm talking about this.
Oh, okay.
I'm talking about this. Like we've all seen this, right? Like this is a familiar sight, right? Like
Right.
at sunset, like the bottom of the clouds are like going to be like pinkish, orangish, yellowish, and the top of the clouds will be grayish, kind of dark, right?
Right. Right.
And similarly, you could look at this from from an airplane. And like, if,
Right.
I don't know if you've had the luxury of seeing this from an airplane, but it's like really beautiful actually. Like you can see that like the bottom of the clouds are illuminated and the tops of the clouds are dark, right? Because of the sunset.
Okay.
So what I want to understand is, how is it that the sun, which is supposed to be above the clouds, otherwise you could like fly into the sun with an airplane, the sun, which is supposed to be above the clouds, I don't understand how on a flat earth the sun could send light to the bottom of the clouds without also illuminating the top of the clouds.
Okay.
Make that make sense.
Okay. So I'm just coming up with this right now because I hadn't thought of that yet. But so because the sun is so far away, it just appears that way because it's spinning around above a flat Earth.
So is the sun actually above the clouds, or is it actually lower than the clouds?
It's above the clouds.
So if it's actually above the clouds, then I don't understand how it being above the clouds could ever make it so that the bottom of the clouds is brighter than the top of the clouds. Right? Like light is traveling from the sun to the clouds. So you'd think that if it's above the clouds, the top should always be brighter than the bottom.
Well, let's see. But that I don't really know. That's kind of outside of my range of knowledge.
But
I'm not really sure.
It's not complicated, right? Like if you put like if I have a light bulb, so I have a table like right here. If I put a light bulb, regardless of how far away I put the light bulb, if I put the light bulb, if it's like my table's, I don't know, 2.5 feet above the ground or something, maybe 3 feet above the ground. If I put the light bulb on the ceiling, regardless of how far away it is, the top of the table will always be brighter than the bottom of the table, right? And similarly, if I put the light bulb on the ground, regardless of how far away I put it, the bottom of the table will always be brighter than the top of the table, just because like the light coming from the light bulb will get to the bottom of the table, but the only way it could get to the top of the table is maybe by reflecting off of something. And when it reflects, it doesn't reflect all of the light, it reflects like part of the light or some of the light, right? So the bottom will always be brighter than the top if the light bulb's on the ground. The top will always be brighter than the bottom if the light is on the ceiling, regardless of how far away the light is. So I don't see how you could ever have the bottoms being brighter than the top if the sun is always higher than the clouds.
Okay, because it's sideways to the clouds. But I just thought of something. So
it's sideways to the clouds?
Okay.
Can you explain what you mean by that?
Okay, so if the Earth is flat, and then the sun rotates above the Earth like a giant superconductor, and it moves to the side.
Like it goes like this, and like the Earth is like here, right?
It rotates,
yeah, sure.
right? Yeah. So that means that's the light shines through the clouds and then kind of like heats it up like almost like a charcoal. So that's why it looks like that.
Wait a minute.
And,
so you think that the clouds are glowing because they're like hot?
No, but just to the light. Well, I mean, it is heat too because the sun puts off energy as well.
Right, but like so like when charcoal glows, it glows because it's like thousands of degrees, right?
Well, according to science.
Do you think that charcoal glows because of some other reason?
Oh yeah, thousands of degrees. I'm sorry.
So charcoal glows because it's very, very hot. But like clouds are not very, very hot. They don't glow because they're hot. The bottoms of the cloud, when you're, so for example, when you're like at noon, if you're like in the air, if you're like in an airplane and it's like noon, the top of the clouds will be very bright and the bottoms of the clouds will be darker. So it's not like the top of the clouds are bright because they're hot. The top of the clouds are bright because the sunlight is hitting the clouds and then bouncing off of the clouds and getting to your eyeballs. So similarly at sunset, the bottoms of the clouds are bright because the sunlight is getting to the bottom of the clouds, bouncing off the clouds, and then getting to your eyeballs. And the top of the clouds are dark because not as much light is getting to the tops of the clouds as is getting to the bottom of the clouds.
Okay, but so it's kind of the same thing because if the sun was above it, the clouds be white because the lights shine directly.
Well,
on
it might be like reddish, depending on like whether or not it's like sunset or whatever. It'll be like reddish or whatever because the further away the sun gets, the more atmosphere it passes through and it filters out more of the blue light. But that's neither here nor there.
Okay, okay. But I mean, it could work the same with flat Earth because if the sun is an angle, is at like on the side of the clouds, then it's going
But
to
it still
shine
won't
through
get
the
to the
clouds.
bottom, right?
And
It'll still get more to the top than it would to the bottom.
No, not necessarily.
Sure it would.
Because if it's directly to the side.
But it's not directly to the side. It's to the side and slightly up.
But according to flat Earth, if it's the side,
according to the
shine
flat Earth,
through.
it's not directly to the side. It's to the side and up.
Okay, slightly, but a lot less than the scientists.
Well, I mean, that just depends on how high you think the sun is. But like, the point is that it will always be it'll always be higher, more higher. It'll always be higher than the clouds are. So the clouds should always be brighter, even if just a little bit. The clouds should always be brighter at the top than it is at the bottom. Because the light is coming down at the clouds, not up at the clouds.
But you only showed me a picture of the top, so I mean, I couldn't see the
Well,
bottom.
I mean, I showed you a picture of the bottom here too.
Oh.
Right, these are the bottoms of the clouds, and you can see how the tops are gray. How they're like
well,
darker.
I mean, if the sun was local, it would look. That's how I think it would look.
Why would the bottoms of the clouds be lighter than the tops of the clouds?
Because the sun is closer to it, and so
the sun is close. The sun is closer to the tops of the clouds.
No, but in the flat Earth theory.
No, I know. On the flat Earth, the sun is closer to the tops of the clouds because the sun is above them.
Yeah, but if it's in the distance,
it's
then
still
it's
still slightly closer to the top than it is to the bottom.
Okay, but slightly though. It's not that much.
Yeah. So the tops of the clouds should be slightly brighter than the bottoms of the clouds.
Wait, say that again.
The tops of the clouds at sunset, the tops of the clouds should be slightly brighter than the bottoms of the clouds.
No, because the sun is let me think. It's because the clouds are in front of the sun. That's why. I'm not sure.
The clouds are in front of the sun?
I haven't because you're looking through the clouds to see the sun.
No,
So that's why it appears that way.
this is by the way, this is a lens flare. This is not the sun.
Oh, okay.
The sun is like setting. You can't see the sun in this picture. The sun's like over here.
Okay.
So what you're seeing is and like that's kind of obvious, right? Because like the tops of the roofs of these buildings are dark, but the clouds are still lit, which means that the sun must be like behind them.
Okay. Well, I mean, I was just saying that it could work through. I mean, think about it this way. Okay, talk about the sun. What about crepuscular rays and sun?
Hold on, don't change topics.
Well, it's related.
It's not related to why the bottoms of the clouds are illuminated.
Well, I just said it's because the sun, the local sun, can work the same.
The local sun, no, it can't. And I've explained to you now like 4 times why it can't. If the sun is local and it's actually higher than the clouds, right? Like if the sun is say 5 miles up or 50 miles up, however high the sun is, if it's not ever getting lower than the clouds, then the top of the clouds will always be closer to the sun than the bottom of the clouds. And furthermore, there will never be a direct line of sight from the sun to the bottom of the clouds, but there will be a direct line of sight from the sun to the top of the clouds. So the top of the clouds are closer and they're within direct line of sight from the sun, always, regardless of how far away the sun is. And the bottoms of the clouds are never in direct line of sight as the sun, and they're always further away from the sun. So they should always be darker on a flat Earth.
Oh, okay, I get it now. It's because the sun is moving so far away that it changes the angle.
The angle does change as it gets further away on a flat Earth. It just so when it's directly above, it's straight down, right? And then as it gets further away, it'll get like less and less steep, right? The angle of the sun rays to the clouds, but it'll never get to zero.
Right.
It'll never get to zero, right? It'll just get like really, really shallow.
No, well, if it's far enough away, you can't see it anymore.
Will the sun ever get to zero angle relative to the clouds like the sun rays?
Because
the sun rays, they just go in a straight line, right? They go out from the sun in all directions in straight lines, basically.
Right.
So like the sun, so if the sun is slightly above the clouds, or if the sun is above the clouds at any amount, regardless of how far away it is, the angle will always be slightly downward.
But it's so far away that your eyes can't. It's like an optical illusion, just like a mirage.
Oh, I don't care what our eyes are doing. I'm just thinking about what direction the sun rays are doing. The sun rays will always be pointing downward slightly, right? Like that's just the real world. What our eyes see, whatever. Like the real world is that the sun rays will always be slightly pointed down.
Why would they be slightly pointed down?
Because I mean, not all of the sun rays will be, but the sun rays that get to the clouds will always be slightly pointed down because the clouds are below the sun. They're at a lower altitude.
I don't know if that's true because, I think it's tricky because when
Want me to draw you a
things get
diagram?
that far away. Okay, sure, go ahead.
Okay. Diagrams are great. I just need to start saving these diagrams because I end up drawing them for a lot of flat earthers. Okay, so we're gonna pretend that the Earth is flat for a minute.
Okay.
And this is not going to be to scale, but it'll be as close to like the Earth is obviously very big, so it's hard to draw like the actual size of the Earth. But so this is like the flat Earth, and I'm gonna put like I'm gonna draw like a little cloud over on the left side here. Draw like a little cloud. Right, you can't see this, but there's like a little cloud over there.
I see it.
Okay, so there's the little cloud.
Okay.
And I'm just drawing it gray. I'm just drawing it gray so that you can see it, and then we'll talk about how it's illuminated. I'm gonna draw the sun as far away from it as I can. So I'm gonna draw the sun over on the side. Let's just draw a little circle, and the sun should be higher than the cloud, right? And maybe it's I don't know how high it is, but like maybe it's like there. And so it just moves sideways over the course of a day, right? And obviously this is just like a side view. It's not like a top-down view. So like in your view, like it's going around in a circle. But like from the side, it just looks like it's going further away and then closer and then, you know, like that, okay?
I get it.
So I'm just going to take this. I'm just going to like put it way over here. Just so it's like as far away as I can possibly draw it. And I'm also going to make it, it's not actually nighttime, but it'll be easier to see what's going on if it's nighttime. So like, because then I'm going to draw the sun rays. So, okay, there's the sun. Now the sun rays, they go out in all directions, right? They spread out in all directions from the sun, so, you know, the sun, oops, I should draw that thicker. You have a sun ray that goes that way, a sun ray that goes that way, sun ray that goes that way,
Okay.
And, you know, so they go out in all directions from the sun. And so I'm actually going to draw more of them pointing towards the cloud just because it's easy, just because that's the thing that we care about. But I am just drawing straight lines out from the middle of the sun. So I'm going to stop them when they get to the cloud, by the way.
Okay.
Because the cloud, you know, it's water vapor and, you know, it'll block some of the sun because that's why the clouds can block the sun, right?
Right.
I'm just drawing a lot at this, like over here.
Okay. I think I get the picture.
Yeah, okay. So now let's zoom in and let's look at the cloud. So from the cloud's perspective, the sun rays are always coming in at a slightly downward angle. Now they're very the angle's small, like it's almost perfectly flat, but they're not perfectly flat. They're coming down at a slight angle downwards. And so what you'll see is that some of these sun rays, they can actually reach the top of the cloud, but none of them can reach the bottom. At best, they'll pass underneath the cloud, right? They can pass underneath the cloud, no problem. But they won't, like this part of the cloud, let me just draw a circle around it. This part of the cloud will never be illuminated by the sun, right?
Okay.
And it doesn't matter how far away I put the sun, it'll never be able to reach that part of the cloud. So that very bottom bit, I should really draw like that very bottom bit, that will never get any direct sunlight. The top of the cloud could get direct sunlight depending on the time of day, but at least like the side of the top side of the cloud that's facing the sun, like this, perhaps this side, that's going to get direct sunlight the whole time, right? So the issue is that somehow when we go look at real world pictures, you know, when we go look at real world pictures like this one, the bottoms of the clouds, the actual bottoms of the clouds are getting sunlight, even though they shouldn't be.
Okay.
Somehow, something's not adding up. Right?
Right.
That's the issue. Well, this is the flat Earth model, right? That's the issue.
Well, it's kind of a basic one. It didn't show how the sun spins around. It goes
well,
in a
yeah.
circle,
This is just a side. It's just a side view.
I understand your argument.
Yeah.
Okay, so it's because as the sun gets farther away, the the clouds relative to you on the Earth are at a certain angle where the sun hits the clouds that way. If that makes sense.
If I'm standing here, I'm gonna draw myself as a little blue guy. I'm standing here, obviously not to scale. I'm not enormous.
Right.
But if this is me, how does me, like, I could move myself around, like wherever you, let's just pretend that I'm like a blob, right? This is me. I could move me around, regardless of where I'm standing. That bottom of the cloud is never going to be illuminated, right?
Well, okay. Well, maybe you should change the model because that's not an exact like flat Earth model. So maybe
this is a side view of the flat Earth.
Okay. So, but put the little person behind the cloud. Okay.
Like
to the left.
Wait. Yeah, like over here.
Okay. So from that angle.
Yeah, over here. Let's say.
The sun from that angle, the sun hits the clouds that way.
Well, wait. That part that's circled is still not getting any light to it.
Well, the sun is producing light like all encompassingly, right? It's not just like
so what you will see is that like what you'll see is that this side of the cloud is illuminated.
Right.
What you'll see is that the top of the cloud is illuminated, but you'll never see the bottom of the cloud be illuminated.
Well, it's just the angle of how when the sun gets far enough away from the clouds.
It doesn't matter how far away the sun gets. It'll always be the case that the side facing the sun will get illuminated, and the top of the cloud will get illuminated, but the bottom will never get illuminated.
But what if the sun was lower because it's farther away?
So do you think that the sun actually gets lower? Like, do you think that its altitude changes?
No, but it's just the perspective of the person.
Right. But we're talking about the actual height of the sun above the ground. If the height of the sun above the ground doesn't change, then it doesn't matter what perspective says or what your eyeballs think is going on. It's just true that none of the light gets to the bottom of your cloud.
I just explained it. I mean, when the sun, it's the angle. Okay, I don't know. I mean, I try to explain it, but you're not really. I don't feel like you're listening. Like you're not really listening to my argument.
So look, is there any way that the light can get to the bottom of the cloud?
Yes.
Okay, so light travels in straight lines, basically, right? Like obviously, like light bends when it enters water,
Parallel,
but
yes.
Yeah,
right.
It travels in straight lines. So, okay, so let's say light gets to the bottom of the clouds. It's here, say. Let's say light gets to here. So if it travels in a straight line, where does it come from?
It comes from behind the clouds.
Which direction? Left, right, up, or down?
Right.
Okay, so it comes from this direction.
Yes.
Okay, now so I'm just gonna keep zooming out. Which direction does it come from? Does it come from the sun?
It's a matter of perspective. So this
well, no, I mean that light ray came from somewhere. It's not a matter that's not a matter of perspective. That light ray came from somewhere. So where did it come from?
It came from the sun.
Okay, so if it came from the sun, let's zoom back in. Well, now that means that it's passing through the cloud, right? In order to get there, it had to pass through the cloud.
You wouldn't be able to see it if it couldn't pass through the cloud.
The point is that the light that passes through the cloud is going to be dimmer than the light that hits the cloud directly.
That doesn't make sense because why would it be dimmer?
Because the cloud absorbs some of the light. That's how, like, clouds can block sunlight, right? That's what clouds do when it's shady.
To a certain extent, but they also...
So that means that the light that gets here is going to be, it's because it has to pass through the cloud to get there, it will be less bright than the light that doesn't have to get through the cloud to get there.
That doesn't make sense. Like,
which part?
Why wouldn't it be brighter at the bottom if the sun was it was like lower behind on the horizon?
Because in order to get to the bottom, again, we can just start there. In order to get to the bottom from the sun, it has to pass through all of that cloud, and that cloud is going to absorb some of that light.
Right.
So look how much cloud it has to pass through.
Different shape of the picture has a different shape of a cloud. It's very flat, and
I mean, I just drew like a blob. But the point is regardless of the shape of the cloud, the bottom will never get illuminated. At least not in direct sunlight, whereas the top can get illuminated in direct sunlight.
They look the same to me, according to the model. I don't know. I kind of feel like we're going in circles on this one.
I mean, this is a problem for, like, surely you agree that if the light, and by the way, notice how the light, how the light that gets to this part of the cloud, notice how it's coming down at an angle?
Okay.
So that means that regardless of how far away the sun is, any light that gets to any part of the cloud, whether it passes through the cloud or not, must be coming down at an angle. Which means that if it is indeed coming down at an angle, then the top part will get direct sunlight, and the bottom part will get indirect sunlight, if it gets any sunlight at all. Because it's coming down at an angle.
Well, yeah, but it's much slighter than the scientific version.
What?
So the scientific version, it would be way above, right? So how does that make sense?
Well, look, okay, so we agree that it must be coming down at an angle on a flat Earth. Now, on a globe,
okay, slightly. Okay.
Yeah. When the sun is far away, it's coming down at a slight angle, but it's still coming down at an angle. Now, I can show you what it would look like on a globe. Actually, I'll just draw you a diagram rather than Googling it, because I haven't been able to find a good Google diagram. So let me draw you a diagram.
Okay.
And I should just save these at some point. That would be the smart thing to do. But anyway, okay, so we have, and obviously this is going to be not to scale because, you know, it's hard to draw things to scale. So here's our Earth, right? And I'm gonna, let's just make it green. Let's pretend there's no water. So I'm gonna draw some clouds. I'm just gonna draw them as like blue blobs because it's just easier. Or I'll draw them as gray blobs rather.
Actually.
Like like here's one, and then I'm just gonna put clouds all around the Earth.
Mm-hmm.
Right?
Maybe make them. Okay, sure.
I'm trying my best to make them roughly cloud shaped, but see how they're
I was just thinking make them flat. That way it matches the picture better. But it's okay.
And then like, you know, there might be a cloud here, and it would be like a. Okay, so see how they're like it's not perfect, but you get the gist, right?
Okay, sure.
They're always like kind of like oriented the same way as the ground. So yeah. Okay, now I think I need probably a few more on the other side too to make my point.
Okay, that's fine.
So let's put one like here, and then we'll put like one over here. So far so good. Okay.
Sure, no problem.
Now, so the sun in the globe model, and I'll zoom in again. The sun in the globe model is very big and very far away. So the light rays are coming in. Basically, yeah. So why can't I draw a line? Okay, there we go. So light rays are coming in basically straight, and so basically parallel to one another. I'm trying to make these parallel. It's not going to be perfect, but
that's fine.
And I'm just going to stop them when they hit clouds. We'll just pretend that they're like rain clouds or whatever. Put one like, it should be like there. And but there'll also be like ones that go like this direction. That's if we, I'm spreading them out in like a suggestive way.
Okay.
Just so you can see what is going on. So we have sun rays coming in, you know, they're all coming in from this direction. And then there's obviously more over here. So on the globe model, this person is experiencing, the person that's over here is experiencing, oh, you know what I should do? I should make the background black again. That was actually really good. There we go. That's really good. So this person is experiencing noon because the sun rays are coming down directly above the clouds, right?
Right.
But because so keep in mind, the Earth is spinning, right? The sun rays are staying in the same direction, but the Earth is spinning. And so this person over here, these people are experiencing sunset because notice how the bottom of this cloud is illuminated?
Right.
Over here. The bottom of that cloud is illuminated. The front edge of this cloud is illuminated. It's sort of the bottom. It'll be like more of the edge, but the bottom of this one will be illuminated. And so, and you know, on this one here, it'll be like afternoon because the sun is still like coming down at an angle, but it's still like kind of coming down from above the clouds. And so on the globe, it makes perfect sense why at sunset, which would be like for this person over here, at sunset, the bottoms of the clouds will be illuminated, but the tops won't be, right? Because there's no sun ray that I could draw that would connect the top of this cloud and points in the same direction without passing through the cloud itself, right? See how it passes through? So in this case, it makes perfect sense that like on a globe, it makes perfect sense that the bottoms of the clouds are illuminated, but the tops of the clouds are not during sunrise and sunset. And yet you can still have the tops of the clouds be illuminated during the middle of the day. So on a globe, that's why this works. On a flat Earth, I don't see how it can work. Like the diagram just doesn't make sense on a flat Earth.
Okay. I haven't done enough research into, or I haven't thought enough about like the way the sun hits the clouds and all those different ways enough to like really win that argument. So I'm just going to concede on that one.
But look, I'm not asking you that you have to change your view.
Okay.
I'm not asking you to change your view. Just think about it. Just think about it.
Okay.
Like,
all right.
And like try to be like open. Like think about like is there really like a way that you can make sense of this without it being like super like overly convoluted on a flat Earth? Because generally the simplest answer is the correct answer usually.
Well, not always.
Well, not always, but usually.
Okay, usually. I agree with that. Yeah, I mean that does make sense. Your model makes sense, and I think it probably does add up. But I mean, I don't think that's true. I still think it's that the Earth is flat. I mean, I think they both make sense to me, but just because the way the sun rotates like above the Earth, then it changes the like because optics aren't perfect even in a camera. I don't know, maybe anyways, but like I said, I have to work on that one because I have some arguments, but I haven't figured out every single argument about flat Earth. So okay. I don't really know I don't know the math enough to show you, but.
Well, I mean, look, I'm not asking for math. It's just like the diagrams, like the diagrams are pretty. They just seem pretty killer to me. And like, by the way, this is like generally true. Like if you agree that light is going to generally travel, like it's not perfect, but it's basically going to travel in a straight line. If you agree with that, then like nothing makes sense on a flat Earth. Like there's like nothing that, and the clouds thing, it's just like, I give that as an example because it's accessible and because everybody's seen this. But like, why can't we see the sun at midnight? Like if the sun is above us, it's like, you know, however many miles above the ground. Like what's stopping the sun rays from getting from the sun to my eyeballs? Like that's.
Well, it's a different
what's
sun.
the explanation?
I think you're still going by the round Earth model for the sun.
No, I'm talking about the flat Earth now. The sun is, you know, maybe it's 500 miles up or whatever, and it's 5,000 miles away.
I think it's like 65.
Okay, let's say it's 65 miles up and it's 5,000 miles, you know, east or west or whatever. Right. Like what's stopping? It's still 65 miles up. What's stopping those sun rays from getting from the sun to my eyeballs?
But the thing is, it's not the science sun. It's not infinite.
I don't know what you mean by it's not the science sun. Like it's a thing and it gives off light in all directions, right?
It's not a million times the size of the Earth.
I'm not saying that it's huge. It doesn't have to be. The point, like even if it was the size of a light bulb, it's really bright, right? It's so bright. So why can't I see?
Vision.
That's irrelevant. The point is it's really bright, right? It's really bright. So why is it that like what's stopping the sun rays from getting from the sun to my eyeball at night?
Can you see a light bulb from 100 miles away?
No, but that's because it's too dim, not because it's being blocked. But the sun, we've all seen a sunset. The sun doesn't. It's not just like fading out. It just gets lower in the sky. It just looks like something's blocking it.
That's an optical illusion.
Okay, so then what is preventing the sunlight from getting from the eyeball or from getting from the sun to my eyeball?
Because it's too dim. It's like a giant light bulb.
If it was a result of dimness, we should see it getting dimmer as it gets like, you know, we should see it fading away over the course of a day. Right? But it doesn't fade away. No, it doesn't.
Okay.
It like for example, 30 minutes or 20 minutes before sunset, you can still see the whole disk, right? Like it's still like fully above the horizon.
Right.
And then like during sunset, like at the very middle of sunset, you can only see half of it. But the brightness of the sun is almost unchanged between the two.
I would disagree because the sky starts to get darker as the sun gets farther away.
That only happens after the sun is already below the horizon. I'm talking
No,
about
I mean,
exactly at sunset.
I was in my apartment last night, and it was like 8 o'clock. The sun hadn't gone down yet, and the sky was starting to get darker.
Right,
So-
but the sun, the actual sun, is the same brightness. Like you could just look at it, and it's like the same brightness when it's halfway obstructed, as opposed to when it's like fully above the.
But it's also
the horizon.
smaller. So how
No,
does
it's
that
not.
make sense?
It's the same size.
I've seen a video of a vanishing point where
Let me
it's
show you.
smaller and then.
They probably didn't
That's
use a
not-
solar filter, but I can show you what I'm talking about.
Okay.
A solar filter. So the thing is like the sun is really bright, and so if you don't have a solar filter on, there will be glare for cameras, and so.
Okay.
But I can show you.
That sounds like an excuse. But.
No, I mean like this is a real thing. Like right, like you know that like on cameras,
Well, I mean,
glare is a thing. Yeah.
So are pictures of the Earth. I mean, they could have made that up.
So are pictures. What are you talking about?
Pictures of the Earth are fake.
Well, I know that you believe that, but like, look, all I'm saying is that like you agree that if you tried to take your phone and take a picture of the sun, there'd be glare, right? Like you would see like a starburst.
Okay, sure.
So you put a solar filter on so you can see the actual disk of the sun, and what you see is that disk size doesn't significantly change size over the course of a day. So this is a video that some guy took from sunrise to sunset. He has a solar filter on his camera, and he's just basically tracking the sun over the course of a day. And you can see what time it is in the upper right hand corner. So right now it's like 7:30, and you can see that, you know, the sun is 684 pixels across, right? And so I'm not going to make you watch the whole thing, but like now it's you know, 10 a.m. and it's 680. I don't know if you can see this. It's 684 pixels across. And then we can keep watching. You know, we can skip forward. Now it's noon, so it's like directly overhead, which is when it should be closest, by the way. So it's when it should be biggest. It's still 684 pixels across. And then we can zoom forward to like say 3 p.m. Now it's still 684 pixels across, even though it's further away. It should be smaller, but it's not. We can zoom forward even more to like 6 p.m. Now it's 6 p.m. and it's 682. If we hit play, it's like fluctuating between 682, 684 pixels across, so it's the same size. And then as we get closer and closer to sunset, so now we're approaching sunset, notice how it's like compressed, how it's like not perfectly round. I don't know if you can see this, but like notice how there's like a little gap at the top and a little gap at the bottom, but there's no gaps on the sides. That's because it's being compressed vertically. And so we'll see that in a minute. But if I let this play, over the course of the sunset, you can see it getting compressed more and more vertically, but its horizontal width is unchanged. It's still 680-ish or 685-ish pixels across. In this case, it's actually slightly larger, but that's, you know, a fitting issue. And so what we see is that the width of the sun is always 685-ish pixels across. But as the sun gets lower, it does shrink in the vertical direction. That's due to atmospheric effects, and that's the kind of thing that you're talking about. But this is seconds before sunset, right? Sunset is happening. Sunset's happening right now, and it's still the exact same width. It's still 685-ish pixels across, right? The whole time it's 685 pixels across. Here, look, so they've taken off the solar filter now. Here, it's 680 pixels across. And then obviously as the sun gets lower, you're seeing less of it, so it's gonna get less wide. But the point is throughout the entire day, the moment it's fully above the horizon, it is basically 685 pixels across the entire day. It doesn't change size. So if it were getting further away, you would think that it would get bigger until it got to noon, and then it would get smaller, but we don't see that.
Well, I mean, there are videos of the vanishing point, but
not with solar filters. There aren't.
I'm not. Okay, well, maybe the solar filter shows the sun I didn't say the sun changes size. I just said that as the sun moves farther away, it gets smaller.
But it doesn't. Like this. So this is showing the actual picture, the actual size of the sun.
Well, yeah,
that's what the solar filter does.
If you use a telescope with the sun filter,
this isn't a telescope. It's just a camera, by the way.
Okay, if you use a camera with the sun filter, obviously, like
the size doesn't change. So that means that from the perspective of your camera, for example, the sun's size completely unchanged regardless of how far away it's going from you. That doesn't make any sense. It should be getting smaller if it's getting further away.
Well, I mean, we already established. Well, I already said that like videos could be made up. So I don't really trust videos because I've seen too many trying to say that the Earth is round, and like for instance,
So
like
then,
the one.
so then there's no evidence I can give you.
There's also videos. Well, I mean, if I feel like I've made sense pretty well.
But
so
it seems
far.
like there's no evidence I can give you because you'll just be like, oh, that's fake. I don't trust that.
I mean, there's
like
okay,
you can do this yourself. Solar filters are not expensive. You can buy them on eBay for like $5. Just get a camera. Like, you know, you can. I don't know if they make solar filters for your phone, but you know your phone has software in it anyway. So just get a camera, buy a solar filter for it. You could do this yourself, and you'll find that its size doesn't change.
Okay, well, I could try that later.
In fact, I have a telescope that I recently got. It has a solar filter, and I could go out and do this right now. I'm not going to because I'm busy, but like I could go out and do this right now. And I'm inside, so obviously I can't point the telescope, and I actually don't know how to connect the telescope to my computer. But like this is something that we could, like you or I, both of us could do it.
Well, he could have been like zooming in with the camera as the sun got farther away. Because
So then look, if you don't believe this,
video.
if you don't believe this, then you can do it yourself. Don't touch
I'm not gonna do it right now either, but
all you got to do is get your camera, and you don't even have to do it over the course of the full day. Just get your camera. Don't adjust the settings at all. Don't put it on auto mode or anything. Just make sure that put the solar filter on, point it at the sun, make sure it's in focus, and then just take a picture every hour, and then compare the size of the sun in each of the pictures. You'll find that it's unchanged.
Okay. Well.
All right. I'm going to let you go, because I think this is probably a good place to stop. But Caleb, seriously.
I have other arguments.
I know, but you've been on for over an hour.
Okay. Oh, damn. All right.
Yeah.
All right,
actually, you've been on for 45 minutes. It's my bad.
I enjoyed that, so I appreciate it.
Well, I'm glad. So, Caleb, seriously, it's so easy. Just get a camera, get a solar filter. Like, I don't know, cameras these days might be expensive, but find a camera. Solar filter's like $5. Just do it yourself. It's so easy to do.
Okay.
All right, Caleb, thank you so much for being here. Have a good one.
Of course. You too.
All right, let's read some super chats and then we'll move on to our next guest. From Tim Davidson with the $2, they don't know relative means looking from. That's true. Maybe I should start defining that because that's a good point. From Brian Peck with the $5, how fast do you have to go to see curve? If triangle is your favorite color, how many pancakes to shingles the roof? Yeah, I was a little bit confused by that too. From Carl Grimes with the $10, the callers show how truly worried we should be for the future of the species. The US is doomed for sure if apocalyptic flat earthers remain in charge of our government. I don't know if there are any flat earthers in charge of our government, but I wouldn't be surprised if there was at least one. And from Shag, though, with the $2, I don't believe videos because I saw videos. That was, look, I didn't want to call him on it. He was a nice guy. All right, let's talk to I Am the I Am. I think I've spoken with him recently, but I don't know if I've spoken with him about the shape of the Earth. I Am the I Am. How's it going?
It's going interesting.
I'm glad to hear it. I Am. Have we spoken recently about the shape of the Earth?
Yes, we think we spoke something regarding to proving God exists.
Oh, but that wasn't about the shape of the Earth, right?
No.
Okay, great. What shape do you think the Earth is?
Well, I don't know. But I felt like, based upon the model you have proposed and to the argument that you have bring regarding to how could the red light hit the bottom of the how could the light hit the bottom of the cloud, and you were constantly evoking an answer for that question from him, but he was unable to give you an answer for that. But you bear in consideration that the light coming from the sun is traveling immense distance, traveling vast distance, right?
How vast?
Well, I don't know the figure off the top of my head, but I know it.
Are we talking like thousands of miles, millions of miles, what billions of miles? What are you doing?
Well, if you take 8-point-something minutes and travel 300 million meters per second, then I think I can
93 million miles. Yep.
Right? Yeah,
roughly.
Yeah. Yeah. Okay. But when it hit the Earth's atmosphere, it's going to experience atmospheric refraction.
To a certain extent. It does bend a little bit. Not very much, though.
Yes. Yes, because the hair has an refractive index,
Mhm.
which increase with distance.
Yeah.
Okay, so
Sorry,
the
give me one sec.
further- Yes, okay.
All right, go ahead.
Yes. So because of atmospheric refraction at great increase with distance, you
Mhm.
find out that when the sun is setting, it is possible. All right, this is just what I'm saying. It's possible. Okay, it's possible that most of the red light you see are the lights that actually bouncing off the earth after experience atmospheric refraction.
Yeah,
So
but how
they
does it get
slow
how does
down.
it get to the bottom of the clouds? Because not only does it have to just refract, it has to bend down and then up. And that's tricky.
Okay.
That's
Okay,
tricky.
so-
Like you would need some very, very special atmospheric conditions to make that happen. And the reality is we see this happen literally every single day. So it's not some special atmospheric conditions.
Yeah, so how that happen is that
I am the I am.
on
It
a
sounds like if you think that the sun is 93 million miles away, then it sounds like you're not a flat earther.
Well, okay. Well, I'm just arguing a point here, right? So
Right. So if you're not actually a flat earther, I'm going to let you go.
I don't want to forget the point I'm trying to make.
If
You
you're
know what
not
I
a
mean?
flat
I
earther, I'm
don't-
going to let you go. All right, let's bring up I don't know from Discord. I don't know, you're on the show. Oh, come back. Come back. I don't know, you're on the show. You got to unmute yourself. Okay. Let's bring up North Coastal. North Coastal, you were on the show.
What up, what up?
North Coastal?
Hey, how you doing, brother?
Oh, sorry, they're there. Now I feel terrible because I think
Can you hear me?
I don't know was talking. Yeah, I'm North Coastal, sorry. I'm going to bring up I don't know because I think that they were talking, but I just couldn't hear them. Oh, no, never mind. They weren't unmuted. Yeah, I can hear you, North Coastal. You're good.
Oh, good. Hey, not for nothing. I'm in the live chat on your Discord. Wow,
Mhm.
the hostility, big dog.
I mean, like, look, if you're saying dumb things, expect people to call you out on it. But if you're being normal, like if you're being kind,
Yeah,
and
yeah, no,
normal,
I think
then
I'm being
sure.
absolutely normal. In fact, I ask you to go check it out. Listen, I'm a physics guy. I was in, studied all this stuff, big math person, all of that. Come across some things recently that made me question a lot of my education and what we're taught in school. So I did come
Mhm.
across some discrepancies. Love to run by you. Threw them in the chat and would just like kind of verbalized. There's one thing between answering questions and saying that you're a waste of carbon and shouldn't exist.
Look, if you think that some of the rules have been if you think that some of the rules have been broken, then you should file a complaint or file a report with the
No,
system,
I'm
and
telling
the
you
mods
now
will
they
handle
are.
it.
Yeah, I'm telling you now they are. And if the
Well,
mods are handling
look,
it, I think it's a kind of a
the
disgusting
administration of the server is not my
reflection of
job. I have an admin who handles this, and I have a mod team who handles this.
Cool. Should I
So-
not have brought it up in the beginning of this conversation?
I mean, like, you can. It's just like I'm not
Okay,
going to solve
cool. I
this.
brought it up,
You should
and now
file a
what's up?
ticket. If somebody's being rude, one of the golden rules is be decent. So if somebody's not being decent
Oh,
with you,
yeah,
file a
not
report, and the mod team will handle it.
Okay, cool.
But anyway,
That's good. 'Cause
so
it's like
so
more
you're a
of a
physics
collection
guy,
of
but you
them.
think
It's
that
pretty-
there's
pretty
but
sad.
what's the deal with the? So what shape do you think the Earth is?
You know what? I don't know anymore. I don't quite believe it's a globe. However, I do believe it's a dome above hand. I think that's a lot more likely. The kind of biggest thing that I'm trying to reason with, we are on it. We're supposedly on a ball spinning 1,000 miles an hour, orbiting the sun at 67,000 miles an hour.
Sure, those are the
and
numbers.
chasing through the solar system, chasing the Milky Way, another it's like half a million miles an hour.
Something like that. Yeah.
And-
So what's the
right.
contention here? What's the issue?
So my issue comes across where it's like, why are the stars so consistent? There's no stretching, dysmorphing, nothing.
Why would they? I mean, like, look, it doesn't matter how fast you're going. Like, if a light bulb out in the distance isn't gonna it's not Star Trek. It's not gonna stretch. It's not real. It would just if you're moving relative to something, then that thing will appear to move relative to you, depending on how far away it is and how it's moving, and all these sorts of things. And we can check that indeed the stars are actually moving. They actually do appear to be in different places depending on what year it is.
Right. Well, I mean, they move slightly, but they are still consistent enough to be used for navigation and everything. Let's not say like the Big Dipper is not the Big Dipper every time I go
Well, yeah.
outside.
So the
And
stars
it's
that
one
we
thing
can
to say
see,
like things are far away, right? So it's like if things are far away, I
Things
can
are far
obviously
away.
things will be moved relative. Like I get that and I understand scale, but we're on a rotating, spinning object.
yeah, the
which
rotation we
should,
see. We see the effect
Right.
of the rotation every night. That's why when I went out yesterday to try to, take a picture of Jupiter, like with my telescope, I had like a 30-minute window before Jupiter set. Right, like the reason why stars they rise at one time of day and then they set at another time of day. The reason why that happens is because we're rotating. That is like if it is indeed the case that we're rotating, then we would expect the stars to do that. So like we do see the motion of the rotation. We see that, no problem. We also do see the motion of the Earth going around the sun. That's why we can see some constellations at one time of year and other constellations at the other time of year. Because when we're on the other side of the sun, nighttime is in a different direction. So the direction of nighttime changes, so you're looking at different stars. And we also see the motion of the Earth through the galaxy. We can see this in the apparent motion of the stars themselves. Year over year, if you look on the same day at the same time, the stars will be in slightly different locations depending on what year it is. So like we see all of these effects.
And look at and of course, and I absolutely. I'm not saying the stars never move, but the stars are like almost unbelievably consistent despite the Earth supposedly moving at extreme speeds in multiple directions. The globe answers distance, but the answer depends on stars being so far away that ordinary visual evidence becomes nearly indistinguishable from fixed central a fixed central dome. So I don't I don't know, man. I'm just having
Like,
trouble
so
buying
do you
it.
think
Can you
that
so
do you think
please
that the
can you
models
convince me that
I'm
we're
trying.
spinning enough? And
Do you think that the models that we like the standard physics models, and you say you're a physics guy, so presumably you're familiar with this. The standard physics models, the standard numbers, do you think that those don't match up with our observations? Where'd he go? Where'd he go? Did somebody just ban him? I don't think anybody banned him. Where'd he go? Nerdy, you can't ban people in the middle of a conversation. Unban him. You guys have got to be, like, mods, you got to be less trigger happy with the bans. Now I have to go find and reverse this. North. Okay, revoke ban. There we go. Ban has been revoked. If you're still watching North Coastal, feel free to join. We'll give him a minute to come back. It wasn't Nightbot, no. We'll give him a minute. Hopefully he notices. North Coastal, if you're still watching, you've been unbanned. I'm gonna have a conversation with my mods, don't worry. All right, I don't know if he's coming back. Okay. All right. All right, we have some other guests that we can bring up. Let's read some super chats first. From Geek McLeod. McLeod? From McLeod? Flat Earthers prove themselves wrong all the time with the 2 Canuck bucks. Thank you so much. It's very generous. I appreciate you. From Just Rick, with the, if you studied and understood the spherical shape of the Earth, but now you're doubting that, the solution isn't more YouTube videos, it's more studying. That's true. With the, thank you so much for the Just Rick with the $5. I do appreciate it. It's McLeod. Got it. I had a friend of a friend in an undergrad who was a McLeod. Oh, is he still in the live, or is he still in the? Yeah, he's still here. He's still in the chat. At least he could, in principle, if we can tag him. So maybe he'll come back, but let's bring up our next guest, and then we can bring up North Coastal if he does come back to continue the conversation. All right, let's talk to this person, whoever that is. Tixbuz. I don't know how to pronounce that. Tixbuz, how's it going?
It is going good, bro. I'm not gonna lie.
Glad to hear it. Am I saying your name right? Is it Tixbuz?
It's Tabs, bro.
Tabs. Okay. Tabs.
Yeah.
What shape do you think the Earth is?
I think the Earth is a globe, but nerdy. Yo, you're a bitch for muting me on a TikTok live, bro.
You can't call people a bitch, my guy, especially mods. You can't call mods a bitch. That's why you got muted, my guy. Oh, he was so loud. Okay, well, that's why you got muted. Quit being a shit person. You'll get muted for that kind of stuff. Nerdy's getting all of the hate here. Nerdy, don't worry, you're not in trouble. I just like you're not in trouble. Don't worry. You're not gonna get demodded. North Coastal, you're currently in the live chat. I can see you in the live chat. Join the live stream. I have unbanned you. Don't worry. I'm going to have a conversation with the mods. But come back if you want to finish the conversation. I can see you. Apparently Nerdy hasn't modded on the TikTok in months. That's some grudge. That is really funny, actually. From Secular Felinus with the $5. If the Earth was flat, cats would have knocked everything off the edge by now. That's true. Cats would do that. All right, let us bring up our next guest, since it looks like North Coastal isn't coming back. Let's bring up Jonathan. Jonathan, how's it going?
What up, man? How you doing?
I'm doing all right. Jonathan, what shape do you think the Earth is?
I'm sorry, what'd you say?
What shape do you think the Earth is?
Oh, well, I know the Earth is it's flat and it's like a dome on top.
Okay. Why do you think so?
Well, see, I started off thinking, the Earth was, flat, obviously, because that's what they teach us in school. I'm not one of those, Yeah, I thought it was crazy too.
Wait, hold on. They teach you that the Earth is flat in school?
Well, they obviously don't teach you that it's like, oh, not flat, that it's round. You know what I'm saying?
Okay, yeah,
I
sure.
didn't mean to say that. Well, when you look into NASA, you know, the thing that's supposed to be, you know, showing the Earth and like proving what the Earth looks like the most, you know, that's supposed to be y'all's main, you know.
No, it's not. We've known that the Earth was a globe since like more than 2,000 years before NASA even existed.
If you look into every old picture or of the Earth and stuff, it is not like how it is now.
Here, do you want me to show you something that you might be interested in?
What would I be interested in?
Do you know who Pliny the Elder is?
No, I don't.
So Pliny the Elder, and just in case you don't know, I can show you. I can, you know, back up.
But can I ask, why would NASA...
We'll get there. Hold on.
What?
I just want to show you something first. So, let me pull it up. One sec. Okay. So I'm just going to take you to the Wikipedia page for Pliny the Elder, just so then you know that he's a serious person. So Pliny the Elder, known in English as Pliny the Elder, was a Roman author, naturalist, scientist, naval and army commander of the early Roman Empire, procurator, and friend of the Emperor Vespasian. He wrote the encyclopedic Naturalis Historia, a 37-volume work, blah, blah, blah. He's an important guy, pretty famous. In fact, he's very famous for this particular work that he wrote, Naturalis Historia, which is a natural history. It's a 37-volume work covering a vast array of topics on human knowledge in the natural world, which became an editorial model for encyclopedias. He basically wrote the first encyclopedia. Now, I have a copy, it's an English translation, of course, of this book, of this very first encyclopedia that he wrote. It's the Natural History of Pliny. Now, if we go to page 50, which is actually page 16, and we go to chapter 2, he talks about of the form of the world. Now, keep in mind, this was written about 2,000-ish years ago. Now, he says in his book, written 2,000 years ago, that it has the form of a perfect globe. We learn from the name which has been uniformly given to it, as well as from numerous natural arguments. For not only does a figure of this kind return everywhere into itself and sustain itself, and also including itself, requiring no adjustments, not sensible of either end or beginning in any of its parts, and is best fitted for that motion, with which, as will appear hereafter, it is continuously turning round, but still more because we perceive it, by the evidence of the sight, to be in every part convex and central, which could not be the case were it of any other figure. So, this is a guy 2,000 or 1,900-ish years before NASA existed, talking about how the Earth is a globe. So we don't have to talk about NASA to know that the Earth is a globe.
But this was just one guy, though. If you look at like how they made the maps and traveled the world, it was completely different, was it not?
So if you look at ancient cosmologies that either didn't have contact with the Greco-Roman tradition or existed before around 2,300, 2,400 years ago, then yes, they will look like you have a pizza with a dome on top. But by the time we had, by around 2,000 or by around 2,300 years ago, 2,250 or so years ago, that was when, at least in the Greco-Roman culture, they figured out that the Earth was a globe. And this guy was part of that cultural tradition. He's writing about 300 years later, indicating that, yeah, they know the Earth is a globe. And they've known it for hundreds of years at this point. And
so how'd they know that?
With measurements. So in particular, Eratosthenes was the first person to measure the size of the Earth, the radius of the Earth. This is like a known thing.
It's not a scientific guy, but there's literal videos of, you know how they talk about what the curvature per mile, whatever, where you shouldn't be able to see the other side, and you can still see it no matter what.
What do you mean you shouldn't be able to see the other side? I have no idea what you're talking about.
Cause if the Earth was round, there's going to be curvature, obviously.
Yep, and you can see it. If you go high enough, you can see it.
At a certain, like, how long is it where you can't see the other side? How many miles?
Well, you can never see the other side of the Earth. If you're on one side, you can never see the other side because the Earth's in the way.
No. I'm talking, when does it get to the point where you don't see it?
Where you don't see what?
Like the curve, or where you see the curve is what I mean.
So it depends on how good your equipment is. You can definitely see the curve at like 50 to 70,000 feet up with your eyeballs.
Let me tell you this.
Why are you cutting me off when I'm answering your question?
All right, my fault.
So you can definitely see the curve with your eyeballs at 50 to 70,000 feet up. This is what high altitude pilots have said. It's
high altitude.
And it's arguably the case, and this depends on the person. Some regular pilots will say that from their cockpit. I really emphasize that word weird. From their cockpit, some pilots will say, yeah, I can see a tiny bit of curvature from roughly 35 to 40,000 feet up, but that's debatable, and it really depends on how good your eyes are. But you can definitely see it at 70,000 feet up with your eyes, and you can see it with a camera at around 35,000 feet up.
Have you ever looked into the old Nikon cameras?
The Nikon P900s?
Yeah, the ones
yeah,
that
I'm
like
familiar with them. Wait,
See,
hold on. Before you say anything, I'm going to make a prediction that you're going to say that NASA canceled them. NASA forced Nikon to discontinue them because they're proving the Earth wasn't a globe. Is that what you're going to say?
Hey, you're on track, buddy.
It's like I can predict the future.
Hey,
no,
it's
so
like
you know
it's like you know it already, brother.
You know
it already.
The Nikon P. You know why they discontinued the Nikon P900?
Why?
Because Nikon was making the Nikon P1000. It was the next version.
Oh, really?
In the same way that Apple discontinued the iPhone 12 because they made the iPhone 13.
Well, you can't see the stuff like how you used to see.
It's
it on
actually
that
a better camera,
that.
and yeah, you can see the exact same stuff and more.
Yeah, I don't know about that, because when you zoom into an actual star, how they tell you these things look like, they don't look like it. And why is that?
Wait, are you talking about when you're like when it's out of focus, when it like looks like a blob?
No, if you zoom into a star with the old Nikon, cameras,
Nikon,
they look like a energy in water.
Oh,
and
that's when it's out of focus.
This goes into the
that's an out of focus star.
The Bible, this links in with the Bible. If you're a Christian in here, you shouldn't believe the Earth is fucking round.
So I just want to show you something really quick. This might be interesting for you. Let me just see if this is okay. So this might be interesting. I haven't seen this video, but this video, I think it's exactly what we want. So this video is using a Nikon P900, right? It's using a Nikon P900. The video is correct versus incorrect focus and exposure of a star with Nikon P900. So let's watch.
I mean, how the fuck can you be a Christian and believe that Earth is round?
So this is what a correctly focused and exposed star should look like at full zoom. So this is fully zoomed in. I don't even know if you can see this. It's very small. It's fully zoomed in. It's just that little speck, right? That's what a star is supposed to look like when you're fully zoomed in and fully in focus. Now, apparently you can get correct exposure by pointing a flashlight in the lens and then locking the exposure. So that's how you get the correct focus and the correct exposure. People watching on YouTube might have a hard time seeing this. Now, if we turn off exposure lock, the star will start to overexpose, producing glare and appear to increase in size. So now you're letting you're increasing the exposure because there's just not enough light. So it's trying to open up the aperture so that, open up the aperture and let more light come in, which will increase the amount of exposure and produce glare. So let's watch this happen. Okay, so see, now it seems like it's a blob because we are producing glare. That blob there is glare. And now, one sec. If we defocus the camera, we will simply see, this is called a bokeh pattern. And that's what you're referring to. That's what happens when the camera's out of focus. You get this
You believe
blob.
that. You believe when the camera's getting closer.
I have a telescope. I've seen this myself. This isn't closer. This is just changing the focus. You're not zooming anymore. You're just changing the focus.
Changing
it just
the
becomes
focus?
out of, yeah, it just becomes out of focus.
All right. Well, I was gonna ask you though. I know you don't wanna trust in NASA or whatever, even though that's y'all's main
It's literally not our main anything.
Yeah, all right, but looking at that, why did Werner Braun have a Bible verse on?
Because he was a Lutheran.
He was a what?
A Lutheran.
Can you explain what that is to me?
It's a kind of Christian. I think he was a Lutheran. He was either Lutheran or Presbyterian. I think he was Lutheran. Yeah, he was a lifelong practicing Lutheran.
Well, you know, that's what Trump told us too. Trump told us he was Christian. Now look at him, motherfucker's Jewish. I mean, you
What the
really gonna
fuck?
believe what they
Wait,
tell
Trump
us,
is
bro.
Jewish?
Yeah, he's our first Jewish president.
Hell yeah, let's go.
Hell yeah, what the fuck?
I love me some diversity, equity, and inclusion.
I've never heard of
I love
damn.
I
hell
love
yeah
me.
from the-
I love
what
me
the
some.
fuck is going on? Someone
You
get-
know what? Trump represent the Jewish pride. Let's go.
Yes, Trump is Jewish, motherfucker. These
We had our
motherfuckers
first black
in here-
president in 200008. The next
bro,
time we
they
had our
think I'm
first Jewish
playing, bro.
president.
Did they-
Let's
hey,
go.
did y'all not
Hell
see that
yeah.
Jewish-
We got
Wait, did
ourselves
y'all
a
not
Jewish
see-
president. It only
Did y'all
took
not see-
250 years, but we did it. We did it. We did it, boys. We got there.
Trump is not Jewish. His kids and his family are. All right, Trump is not Jewish, guys, but his family is.
Oh, I
And
thought you
his
said that Trump
kids.
was Jewish.
No, that's what they're saying. They're saying Trump.
Wait, is Trump Jewish or is Trump not Jewish now?
Bro, that motherfucker is as Jewish as it gets.
Let's go. First we had our first black president, and then right after we had our first Jewish president.
No!
This is we're fucking
look-
winning on this diversity game. Let's go, USA, USA.
Bro, the thing is, he lured in Christians by saying that. You really believe this guy? This guy's a good guy.
Oh no, but I guess he's Jewish, which means at least we're winning on the diversity front.
Hey, we
Let's
got a
go.
point there.
Love
We got a
me
point
some
there.
love me some Jewish representation.
Yeah. Well, I just think
I don't know about you, but I'm pro inclusion. I'm pro supporting minorities. So like if you're telling me that Trump is our first Jewish president, let's go. Hell yeah. We're letting minorities finally take the reins of power. Let's go.
Oh shit. Well,
are you a minority?
I am.
So you should appreciate it when we have our first Jewish president, just like how it was awesome when we had
Yeah,
our first black president.
satanic fucking president that gets bro.
I thought he was Jewish, not satanic.
Oh, he's both, bro. What? He can be Christian, anything he wants, and satanic. What do you mean?
Wait, so is he Jewish? Is he Christian? Is he satanic? What is he?
Who knows, bro? That's the devil's son right there.
It sounds like you're crashing out over Trump, even though he's not even Jewish.
Yo, Trump is literally Jew, bro.
Wait, he's Jew? He's Jew or he's Jewish? Which one is it?
Oh shit, Jewish, my fault.
Okay, yeah, cool. So Trump is Jewish. So are we talking about some like pro minority representation here? Are we talking like DEI shit? Like we got this on lock?
Yeah, locked.
I'm a progressive dude. I love seeing that kind of representation at the top echelons of power.
Why is that? Not when they're
Because
getting,
it's you know what, man, I love it when we don't just have the white Christian man at the top. I love it when we have black men and when we have Jewish men. I love it when we have women in power. This is great.
What's you against the Christians?
Look, man, they've just been ruling this. They've been the majority. They've been ruling the society for the whole time, man. Like I want to see for once in our life, I want to see the minorities finally get a chance.
Christianity is the truth, brother. Why do you think they try to act like they're Christians?
Why do I think what?
Why do you think they mask themselves as Christians?
Who?
The elites, brother.
The elites?
Yeah, as in Trump.
Wait, was like George Bush not Christian?
Brother.
Do you even remember George Bush?
Oh, you actually got a point right there.
Jonathan, how old are you?
I'm 18.
Okay, so you weren't even alive. Arguably, you weren't even alive for George Bush.
And what the fuck does that change?
Was he not Christian?
Okay.
Okay, so is he one of the elites?
Now that they do I not tell you that they masked
was
Christian?
Joe Biden Christian?
Fuck no, bro.
Bro was like the second Catholic president in American history.
Do you believe that we actually have fucking rights to vote? Do you believe we actually have the power to pick who we want?
Well, I mean, it's a little bit more complicated than like just direct popular vote, but like it seems like that you don't think that like anything is the way that it actually is. So I don't know. You sound like a little confused.
Brother, do you think this world is just like this because have you looked at the fucking Epstein files? That should wake you up enough.
That's rough.
Why the fuck
Trump's
is that
in there
not waking
alive.
you up? Yeah, exactly.
Trump's in there a lot.
Hold on. Do you think these people are killing, eating babies for no reason? No, there's something behind this. There's something satanic behind this.
Well, I don't know
There's
if anybody's
something
eating
spiritual.
babies.
Then what the fuck are they doing?
I mean, like,
Why
it
in the
seems like
fucking
that.
files did they say the babies?
I don't know if there are any babies being eaten in the Epstein files.
Why did they say that babies taste like cream cheese in
I
the
don't
fucking
fucking know,
files?
man. I don't know if that's even in there. Hey, Jonathan. Maybe come back in like 6 to 7 years when your frontal lobe has finished developing.
See, I look for the truth. You're probably looking for
Apparently
just
not.
whatever the fuck, please.
You need to like stick your nose in a book and like just get off
Yes,
the internet
Terry,
for 6 to
Jonathan was
7
there.
years.
Brother,
You just got to get off the internet for like 6 to 7 years. Like that would be so good for your frontal lobe development. Jonathan, I'm going to let you go, but thank you for being here and thank you for crashing out. It was fun. All right, we did get North Coastal is back, so we can bring him up. North Coastal, welcome back. Sorry about that earlier.
Yeah, real embarrassing.
Yeah, I mean they're gonna get a stern talking to. Don't you worry.
Yeah, I hope so.
But yeah,
Your
actually,
moderators
like
are
you should
So
seriously
soft.
consider trying like filing a like if people were being like shitty, file a whatever it's called, like a ticket, and the mods will handle it, and I'll make sure that they
Yeah,
do.
no, I you know what, I don't think they are. The mods are in the chat, and
I will make sure that they handle it. Don't worry.
All right, cool. Yeah.
So
just
file a
look at the
ticket. File a
statements
ticket.
and look
Someone
what's
for being
being
shitty. Anyway,
said.
where were we? What were we talking about?
I don't know, man. Stars and how we're all.
Oh,
moving
yeah,
and
I remember.
everything.
Okay, so I asked you.
I guess what I want to ask is if I want to just kind of, if you don't mind, I want you to put the burden of proof on you. Can you try to convince me? Because I want.
Yeah, sure.
I believe
So
that
first,
even though we're spinning,
Absolutely, I
rotating,
can.
traveling that far, that somehow everything in the distance stays the same.
Absolutely, I can try to. So first, but before we get
These
there,
guys
I just
in the
need to.
chat don't even know how many
I just need to
sexes there
check. North Coastal, you're talking to me now. Before, so just so we're on the same page, do you think that the current models that we use in physics, relativity, gravity, the orbits, all these things, do you think that these models accurately reproduce the data or the observations that we see in the sky with regards to the stars?
I think the math actually does go together. But again,
okay,
if
so the
you're
math
telling me,
works. So
hey,
we agree
look
that
at the numbers.
So there's no actual issue with the current models with the observations that we have of the stars, right? There's no like
all
actual
I'm saying
conflict
is-
there.
There's no conflict with regards to like if we apply these values to these formulas, then yes, everything is
Right.
consistent enough.
Okay,
But my
so-
thing is,
so what's
these
the
values,
problem?
these formula, I'm telling you, these values, these formulas
Mhm.
that are so consistent, I don't think they really line up with observation.
Wait, you just said
Again,
that they.
I still
you,
have
you
to
just
take
said
a
that they
leap.
did.
No, I say that the math works.
So look, you have some laws of motion. You have Newton's laws of motion, right? That's basically all you need for this. You have Newton's laws of motion. You have you have a force. You have a universal force of gravity, which has a formula, and then you can plug in initial conditions. Like you can plug in like the velocity of the Earth relative to the sun or something, and you can plug in the velocity of the sun relative. You can plug all of that in, and that will spit out numbers for how much a given star, for example, should appear to move over the course of a day, or over the course of a year, or whatever. How much the star should appear to change in its location from your perspective on the Earth. Do you think that when you plug in the numbers that the model says are the correct numbers, like the Earth rotates once per day and it's going around the sun at like 65-ish thousand miles an hour, and if you plug in all those numbers, do you think then out will come, this star will rotate at this, will appear to move in the sky at this rate per every hour or whatever, or it'll appear to move at this rate per year or whatever. Do you think that those numbers that it spits out, that the formula spit out, agree with our observations?
Yeah, no, absolutely. And I think they were designed in a way to do so.
Okay,
Like,
so
I
if they
do
agree with our
believe that we have
observations, then the
formulas in order
models,
to-
there's nothing wrong with the
Right.
models. The point
Sure,
is
sure,
that
I guess
given
I'm
the
gonna take
data,
this-
given the input data and the models, they perfectly represent the world around us. So
I think we have
what's the
very good
contention?
models. I'm not arguing that.
So then what's the contention? What's the issue?
Okay,
What's the
so in order
apparent
for these
thing that
models-
looks wrong?
Yep. In order for these models to be accurate and everything, I still have to be convinced that we are actually rotating at this speed, at this direction, moving around this sun, traveling through the galaxy, and I just don't see that. I think there are there's a lot more simple solutions than
Okay, so in
than
some
what's being
sense,
offered.
the fact that the
Am I making
models
sense though? Like,
I think I get what you're saying. In some sense, the fact that the models accurately reproduce our data and there's no our observations, and there's no other model that does, that is in line with like the way that light behaves. Like, for example, we have Maxwell's equations, which describes how light behaves. So because there are no other models that accurately reproduce our observations, and this model does, and this model. And this model has these initial conditions, that is evidence that these initial conditions are correct. That's evidence. It's not proof, of course, but it's evidence. Surely we can agree on that.
No, not necessarily. I think it's proof that the model can work.
I didn't say proof. I said it's evidence. It's evidence evidence that the initial conditions represent reality.
Can you give me an example of a model proving something or showing something true, but not?
I'm giving you evidence. We're not talking about proof here. We're talking about
what's
evidence.
The difference between evidence and proof then? What are you
I thought you were a science guy. I thought you were a physics guy.
No,
evidence,
go ahead. No.
Evidence increases the likelihood that something is true or correct. Proof is like definitive, right?
Mm-hmm.
In science, we work with evidence. We don't work with proof.
Sure.
So all we can do is provide evidence. You could always say, but what if like we're all hallucinating all of the data, right?
Right. Of course. I mean, you can always
we only ever work with evidence.
Like, prove to me that I'm not in a simulation.
So when we have a model, the way that we do science, this is like the fundamental feature of science, is that you have some observation about the world, some perhaps mild observation or novel observation, and you're like, that's weird. I wonder how I can make sense of that. And then you propose a model. And then, given that model, which in this case includes like the initial conditions and then like the force laws and things like this. Given that model, you see if that model makes accurate predictions about some other fact of the observational world, some other thing that we can observe. So maybe the first thing that we observe is we see that like, well, the stars, they appear to rise and set at a certain time, and we see different constellations at different times of year. Maybe that's your observation. So then somebody comes up with this model, maybe call them Copernicus. They come up with this model. They're like, oh, well, the reason why the sun rises and sets, or why the sun rises and sets, the stars rise and set, and yet we see different constellations at different times of year, is because the Earth is going around the sun and the Earth is rotating. And so we take this model and then we plug in, we actually do the math, we do the numbers, and we see if this model were true, what would we observe about the world around us? Like what predictions can we make from this model, and that we can then go test out in the world around us? And one of the predictions that we can make, in fact, this was done in the 1700s, I want to say, one of the predictions that you can make from taking this model of gravity and taking in all of the data that we can observe, is that you can predict that there's another planet out there. You can predict that Neptune exists, in fact, and this was done by, was it Herschel?
Through like gravitational pull and relativity.
Through it's not even through observing gravitational pull. It's just it's indirectly through that, but from observing the motion of the other planets that we can see, and I call them planets. They're just like whatever the lights are in the sky. And so this was predicted. Okay, so I was wrong about the date. This was predicted in the 1840s. And then we pointed a telescope in the direction and we found it. So this is an example of the model making a prediction and the prediction coming true. This is how we do science, and so this is indeed evidence that the model is correct.
Totally dope, and I'm with you. And I like.
So we can agree that this is evidence, right?
Sure, but okay, I'll give you an example of a bad model, bad evidence. What is it called? The body mass index, the BMI.
Sure. What about it?
All right, someone has a very low BMI. That person is strong, lean, and in excellent shape. However, according to the BMI, they're very unhealthy.
Sure. Right.
Okay. So we have evidence that they're unhealthy, because the models and the numbers shows it, and it is relatively consistent. However,
wait, hold on. What's the evidence that what's the evidence that it sounds like what you're presenting is you're presenting evidence against the model, because the model would predict. The model would predict that the person would be unhealthy. Then we go observe reality, and we're like, oh, this person's not unhealthy at all. So that would be evidence against the model. Because the model failed to make an accurate prediction.
Evidence against the model, right?
Right. And so
I think
so
it's
this
easy
isn't
to-
so
go ahead.
that's a great example of the scientific method working. What's the issue?
That's a great example of the scientific method working. Right, but
Yeah.
we can't, I mean, how much, like, to what extent can we actually test these things?
I
Like,
just gave you an example of how we can
I
test
don't
it.
even think
Making the
moon
prediction
landing's
of
there
the
anymore.
existence of Neptune,
I don't know, man.
that's a way
Like,
of
can you-
testing it.
Sure. Well, just tell me why we're spinning and how, like, recap
Look,
that
so
for
so
me.
I just like I like it sounds like you just reset. The point is that
Yeah,
like you're a
it's-
science guy. I
Yeah.
gave you an example, a very specific example, a historical, like real example that actually happened of we had a model, we made some observations, we produced a model, we made predictions based off of that model, and then we checked out in the real world, did those predictions come true? And they did. That is evidence in favor of the model. Which
Well,
means
they
that's evidence in
came
favor
true
of
in
all of the
saying that
things
we
that go into
pointed a
model, including the
telescope in
rotation
one
of the Earth,
direction,
the orbit of
and
the
we're
Earth
saying
around the
that
sun.
this
It's
blur
evidence in
this
favor of all of
light
that.
is Neptune.
Sorry,
So,
go
I
ahead.
mean, yeah, no, I think there's a little delay. I didn't mean to talk over you. Saying, I mean, there's evidence that if we point this telescope in a single direction, there's this blob of light that should be there, that is there, that we're going to call Neptune. I get
Yeah,
that.
we named it.
I'm just
No,
yeah,
it's not
well,
evidence of all that. It's evidence that the model represents reality. That's how we do science. Like you produce a hypothesis, you test the hypothesis. If the hypothesis comes true, then that observation, whatever you made, is evidence of that your hypothesis is true. That's how we do science.
So are we saying that the stars are moving relative with the Earth? So like they're moving as well around it?
Wait, so are you asking whether the stars are moving relative to the Earth? Because yeah,
Yes.
of course they are.
Okay, so are they moving like around it with it? Like I'm
Relative to the
I don't
Earth,
know.
yeah, sure.
I'm
Yeah,
still
relative to the Earth,
struggling
definitely.
finding how. Okay, still struggling finding how.
But
we
like,
could be
look,
moving
you
at all
have
these
to
different
agree
directions at all
that
this different
certainly
speed.
the Neptune
Still
example
be
is
lined up like
evidence
that.
of the entire heliocentric model.
Discovering Neptune through the model prediction using like gravity. Okay, yeah, no, that's awesome. That's badass. We do the same thing with fossils. I think that's cool.
Yeah. So like this
Yeah.
is evidence. Now, it sounds like you want more evidence. I can give you
I
more
do
evidence
want
if you
some more
want.
of it. Yeah, please.
Okay, so the modern description of gravity is uses general relativity, right?
And we really don't have a way to manipulate gravity yet, which is kind of
Sure
weird.
we do. What are you talking about? Of course we do.
Go ahead,
You
show
just
me.
put two masses close to each other, and then the gravitational force between them will get stronger. Like of course we can
don't
manipulate
cha-
gravity.
We don't manipulate gravity.
I don't
mean,
know what
that's
you
how it
mean by
works in theory, and
manipulate
it makes
gravity
sense.
if you don't mean just increase the force or decrease the force.
All right, calm down. I'm pointing out an actual cool physics thing. We don't really have a way to turn up or turn down gravity on will.
We don't have a
without
way to
adding
turn
weight,
up or turn down electromagnetism either.
right? Actually, we do. We just can
How?
add more power to it.
Add more, power? You mean charge?
Yeah. What's
Yeah,
the
so you can
difference?
do the
You know
same
what I
thing
mean?
with gravity, you just add more
Exactly.
mass.
Yeah. Do you think they're related? I actually did see some theories recently
Charge
about
and
gravity
mass are
elect-
not intrinsically related, no.
Nope. Gravity and electromagneticity.
No, they're not intrinsically
seen those
related, no.
No. Okay.
No. But look, so using general relativity, a prediction was made in or more than 100 years ago at this point that there are these things called black holes. That black holes are basically ultra dense collapsed stars that they're so dense that even light travels at a certain speed. They're so dense that light cannot escape them. And so for a long time, we didn't really have any direct evidence that these things existed. And then in 2019, I want to say, we got our first direct image of these things. We can just see them now. I mean, we see them in radio waves. We don't see them with visible light, but we can just see these things now. And they exactly match the predictions of general relativity. So this is another piece of evidence that general relativity is correct.
Yo, can you hear me?
I can hear you now. Yeah, I don't know where you
I
went,
missed the
but
last half. You said it's another
yeah.
piece.
So in 2019 we got our first images of black holes. We got two, one of something called the M87 star, the other one called Sagittarius A star. We imaged these things. These were predicted by general relativity to be black holes, and then we imaged them, and they are black holes. Like they looked exactly as we expected them to be if they were black holes. So this is another piece of evidence, a prediction coming true, made by general relativity, which is, our modern understanding of gravity. So this is a perfect example of the model making predictions, those predictions coming true, and therefore those things are evidence of the model.
Okay. Yeah, I mean, the model does kind of fall apart when it gets to like the beginning, like Big Bang and all that.
Sure. Nobody's making the claim that all models are perfect.
Yeah.
The point is that the models represent reality at certain scales. And so, for example, like general relativity accurately represents reality from scales say the size of large molecules up to the size of galaxies or so. And then at scales larger than galaxies, it's not clear. At scales smaller than a molecule, it's not clear. We don't really know what's going on at those scales, but we have models that make good predictions and have evidence for them like in all of those scales between. So this is evidence of the models.
Okay, so you're proving the models to be true. Okay. All right.
And so
I don't know. I just
look.
Here's
the
get
issue.
it. I agree that the numbers are true.
That's how we do science.
Gravity is absolutely a force. I do think things are relative, and we can absolutely measure and manipulate these things. I'm not arguing that. I'm just saying, taking that step from, hey, look at all these numbers that I have to prove that I'm right. Also,
do you think that the Coriolis effect is real?
One more step of belief that we're also rotating, spinning, moving.
Do you think that the Coriolis effect is real?
The what?
The Coriolis effect.
Explain it. Remind me. Refresh me.
It is a non-inertial force, so it's a result of being in a non-inertial reference frame. It's not like a true force; it's a pseudo force that appears when you're rotating about some axis.
Yeah, I understand. I understand.
I can show you a video if you want to see a nice video.
It's cool. I get that you can only feel movement or acceleration.
That's not really what I'm talking about. I'm talking about it's a specific kind of effect that appears on a non-inertial reference frame, a rotating non-inertial reference frame. So this is a nice video. So you have some people, they're on like a merry-go-round, right? So obviously like the merry-go-round is spinning, and this person in the bottom left is going to try to throw the ball to the person directly across. When they do, okay, hold on. Come on. Actually do it. I don't know what's taking so long to actually do it. Maybe it happened actually earlier. Okay, here we go. They're gonna throw it. They're just gonna push it forward. Oh, and it goes to the person to their right instead of going to the person in front of them. And hopefully they will show a diagram. Okay, so watch. They're just going to push it forward, but somehow it just curves over to the right. That's an example of the Coriolis effect. It's because they're spinning that there is this inertial force, or this inertial pseudo force, that is things tend to not move in straight lines if you're on a rotating thing. And this is the kind of thing that you can calculate, you can exactly account for. This has a formula for it. It's not just like some vague thing.
I think that's no.
Do you think that? So do you think that we can measure the Coriolis effect just sitting on the ground? Just like we're not on a spinning merry-go-round. We're just sitting there on the ground, like in a room. Can we measure the Coriolis effect? Do you think?
I think it can be explained with the effect of like air pressure and weather systems, or like
air pressure and weather systems don't seem like they would affect these things at all. In fact, one of the best demonstrations of the Coriolis effect is produced by something called a Compton generator, which is a device that was invented by Compton. He was a physicist in the early 1900s when he was an undergraduate. And the way that you demonstrate the Coriolis effect is using a sealed circular tube of water. And so you can fill that tube with like little dust particles so that you can see what's going on. And if you take that tube and if you flip it upside down, obviously you build an apparatus so that you don't shake when you're doing it, so that it happens like very smoothly. But if you flip it upside down, what'll start to happen is it'll start to swirl in one particular direction. And this is perfectly explained by the Coriolis effect. It's not explained, you can't account for air pressure because it's a sealed tube. Temperature is not going to prefer it to go in one direction over the other, so that's not going to play a role. So I'm not sure how you're going to account for this, except the Coriolis effect, which again, the mathematics makes the prediction that that the water will start to swirl at exactly the rate that it actually starts to swirl. So again, we have another example of the model, in this case a rotating Earth, making a prediction about a very specific rate at which rate and direction at which water starts to swirl in this kind of device that you can build. It's called a Compton generator, and it exactly matches predictions. So that's evidence for a rotating Earth.
Here, I'm looking at it. Okay, and it is measurable, and you can calculate. Yeah, that makes sense. Yeah. Rotating Earth. Is there any model is there like any very convincing model that that you've come across regarding like not globe?
Nope.
Globe
There's
Earth.
not a single one that can account for example, the effect measured by a Compton generator. And I've talked with thousands of flat earthers. I've spoken with thousands of them.
By the way, I'm not saying I'm a flat earther. I'm just saying I don't really buy.
You're a globe skeptic, which may as well be, right?
Yeah. There you go.
But
lies. Oh my goodness,
it
guys!
I
don't recommend whoever's watching you guys. I really don't recommend joining your channel. I spend nothing but
North Coastal. Here's what I would suggest. I would suggest not typing and having conversations in the Discord chat while also being on a live with me. That's kind of rude.
I would suggest that you have a little bit better of a audience and community. And
I would suggest that you focus on the conversation with me rather than talking to other people while you're on my live show.
Is this not
disrespectful?
Is this not your community? I think it's disrespectful how your community.
You can accuse my community of being whatever. You are currently disrespecting me personally.
I'm not accusing it. I have the evidence.
You are currently disrespecting me personally.
I have the proof too.
North Coastal,
I'm telling
you. Like I'm a person.
So, Blitz,
I'm a person. You're disrespecting me personally.
Let me just get your logic correct, real quick.
You are disrespecting me personally. If you want to make the claim that people were disrespecting you in the Discord chat, that might be true. But you are now currently disrespecting me by having a separate conversation while you are on my live show. You understand?
Do you not find it disrespectful to me that the community you're hosting is this disrespectful? Do you not find that disrespectful to me?
Look, if they're being disrespectful to you, I will have my mods handle it. You've already made that clear that they've been mean to you. So I'm going to make sure that that's handled. But do you understand that you are currently disrespecting me actively? You are doing this to me.
Do you understand? Do you understand it takes respect to get respect?
Have I disrespected you? Have I disrespected you, North Coastal?
Does your community represent
Have I disrespected you, North Coastal?
Does
the question.
Does the community represent you? Is the community a reflection of you?
No. North Coastal,
okay, so
have I disrespected you?
All that they're talking.
Have I disrespected you, North Coastal?
You got me. I got banned.
Have I disrespected you, North Coastal?
Okay.
Answer the question. Have I disrespected you?
Your community.
Have I disrespected you? Stop crying and answer the question.
No one's crying.
You're currently crying because people were being mean to you in a Discord, and I'm currently talking to you. You and I are having a conversation, and in the middle of the conversation, when I'm answering questions that you asked me, I see you typing in the Discord live chat.
Well, why are you checking the live chat if we're talking, bro? You know how disrespectful
because sometimes my mods have to tell me things like, "Oh, hey, you're forgetting about this person in Discord who's been waiting for an hour to come up." By the way, that's the kind of reason why I brought you up initially, because I have to check my Discord server to make sure that people are waiting. So yes, I have the live pulled up, and I can see you typing in it while we're having a conversation, while I'm explaining something to you. So maybe, before you accuse somebody of disrespecting you, maybe show a little respect yourself.
Maybe you should.
He's gone. Probably. I mean, like, we can maybe ban him. Maybe not. We'll have to go over that. But like, bro was just being like super rude to me. And by the way, he's still typing. Let's pull this up just so everybody can see it. Just so you guys, just for the funsies. Here's him saying clowns. By the way, that was 1 minute ago. Before he got banned, before he got booted. And by the way, when I was explaining the Compton generator to him, this is what he read, or this is what he wrote. This was at 12:10, I believe. So at 12:10, he wrote, where is it? Oh, a lot of people are making fun of him in the chat, which you know, I get it now. I get it now. Sorry, here it is. Big time not buying the math anymore. He wrote that while I was talking to him in the Discord live chat. Like, what is he doing? And this was when he was like, oh, like, you know, I didn't follow that. Can you explain it again? Because he wasn't paying attention. He was being rude. He was being disrespectful, if you will. Y'all are great though. This is pretty good. Lamau, you're welcome. I mean, he's still crashing out in the Discord chat. Congrats on being part of the most cringy community there is. Most disrespectful, toxic, hate-filled. By the way, the reason why he was banned, I can just show you guys this. The reason why he was banned initially was because of... was because of this comment. A lot of pride flags going around here. Lol, gay. That's why he was banned, because he was being homophobic. So anyway, and he's still in the live channel. We'll let the live eat him up for a bit. Let's read some super chats, and then I have to end the live because I have to go get a crown placed. So, from Empiricist with the $2, on many levels, FLERFS can't focus. No, we cannot. Oh, he's gone again? He was transphobic when he returned. Oh, cringe. Okay, yeah, good. From Quantum Tap with the $2 Australian, pivot from flat earth to Trump to Jew to Satanist. Wow, yeah, no, is it right? Isn't that crazy? From Icy Spin with the $2, caller gets it. Hell yeah, brother. USA. Yeah, I know, right? Let's go. Jewish Trump, I'm down. Still hate him, but Jewish, yeah, let's go. From Lost in FRP with the 220 Turkish liras. Reminder of a post. Praise be to Allah. President Donald J. Trump. True, he did post that. From Icy Spin with the $2, can you ask next caller to approximate the number of stars? Oh, that'd be I should have done that, but it was too late. All right, y'all. So let me just double check and make sure I haven't missed any cash apps. I have missed some cash apps, by the way. From Grimlock with the $10 for looking directly at the sun in AZ is metal AF. Yeah, don't do that. Oh, okay. Hold on. I thought that was a... Okay, never mind. We're good. All right, y'all. So I'm going to end the live stream here. I got to go get a crown placed. I will be on the line on Skeptalk in about 4 hours or so. So make sure to stop on by. There will be an announcement that goes out in the Discord server. If you're interested in watching that, I will be with Forrest Valkai. So make sure to stop on by. I will see you guys there. Until next time, which is tomorrow.